What if everything you thought you knew about gravity was incomplete? Picture this: space itself isn't just a smooth, invisible fabric, as Einstein described, but a chaotic, seething ocean of tiny, invisible fragments. This isn't science fiction. It's the heart of one of the most profound mysteries in modern physics: quantum gravity. For over a century, scientists have been chasing a theory that can bridge the colossal gap between Einstein's relativity, the rulebook for the cosmos, and the bizarre, probabilistic world of quantum mechanics. And here's the wild part: we still don't have the answer, but the hunt for that answer has led to some of the most thrilling, mind-bending theories ever conceived. Think about gravity for a second. It's the force that holds planets in orbit, keeps your feet on the ground, and even bends light itself. Yet, at the smallest scales where particles flicker in and out of existence and reality itself seems to blur, gravity refuses to play by the rules. Quantum mechanics and relativity, the twin pillars of modern physics, clash violently here, leaving us with a cosmic puzzle so deep that solving it could rewrite our understanding of reality. What if space-time isn't continuous but built from tiny, indivisible pieces? What if black holes aren't just cosmic vacuum cleaners but windows into entirely new dimensions? These aren't just wild guesses, they're serious, cutting-edge theories being tested by some of the brightest minds on the planet. And that's exactly what we're diving into today. From loop quantum gravity to string theory, from holographic universes to the idea that space itself might be an illusion, we're about to explore 30 of the most astonishing theories trying to crack the code of quantum gravity. Some of these ideas will sound like pure fantasy, others might just give you goosebumps, but all of them share one thing in common: they're daring attempts to answer a question that's haunted physicists for generations. So buckle up, because by the end of this journey, you might never look at the universe the same way again. The mysteries of quantum gravity aren't just for scientists in lab coats. They're for anyone who's ever stared at the night sky and wondered what's really holding it all together. Let's start with one of the most radical approaches to quantum gravity: loop quantum gravity. Forget the idea of space-time as a smooth, unbroken fabric. This theory paints a very different picture. Space itself is woven from tiny, vibrating loops like an unimaginably fine mesh. These loops form a network, a kind of cosmic spiderweb where every connection carries a quantum of area or volume. It's as if reality isn't continuous but stitched together from minuscule, indivisible pieces. This idea comes with some mind-blowing implications. For one, singularities, those infinitely dense points at the heart of black holes where Einstein's equations break down, simply can't exist in loop quantum gravity. Instead of collapsing into a mathematical nightmare, matter rebounds at the smallest scales like a cosmic bounce. No infinite densities, no edges of reality, just a dynamic, granular universe where space itself has a built-in resolution limit. One of the leading voices behind this theory is physicist Carlo Rovelli. He and others argue that loop quantum gravity isn't just about reimagining space but also redefining time. In this framework, time doesn't flow like a river but emerges from the way these loops interact. It's a dramatic shift from our everyday intuition, where time feels like a universal backdrop. So what's the catch? Well, loop quantum gravity struggles with explaining how this pixelated space-time gives rise to the smooth, curved geometry Einstein described. And unlike string theory, which we'll get to soon, it hasn't yet made many testable predictions, but it's a bold attempt to solve the quantum gravity puzzle without inventing extra dimensions or unseen particles. It's a theory that says the answers might already be hidden in the very fabric of space itself, if we're willing to look close enough. If loop quantum gravity is right, the Big Bang wasn't a singular explosion from nothing, it was more like a cosmic rebound. Imagine the universe collapsing inward, squeezed to an unimaginable density, only to bounce back outward in a fiery rebirth. This quantum bounce erases the need for a singularity, that baffling point of infinite density where physics simply gives up. Instead, the theory suggests the universe has always existed in some form, cycling through contractions and expansions like a celestial heartbeat. At the heart of this idea is the Planck scale, the smallest possible unit of space, roughly a trillionth of a trillionth the size of an atom. Here, space-time isn't smooth but granular, like a mosaic where each tile is a tiny, vibrating loop. These loops don't just define space, they also dictate how gravity behaves at microscopic levels. Picture a foam of bubbles at the smallest scales, constantly shifting and reconnecting. Gravity, in this view, isn't a force traveling through space. It's the way these loops interact, weaving the fabric of reality itself. But why haven't we detected this quantum foam? The challenge is scale. Probing the Planck length would require energies trillions of times beyond what our most powerful particle colliders can achieve. It's like trying to study the grooves on a vinyl record with a sledgehammer. Our tools are too blunt for such fine detail. Some researchers hope indirect signatures might appear in cosmic microwave background radiation or gravitational waves, subtle fingerprints of a pixelated universe. Others argue that black holes, those extreme gravity laboratories, could reveal clues if their behavior deviates from Einstein's predictions. The theory also reshapes how we think about time. Without a smooth continuum, events might not unfold in a neat, linear sequence. Instead, time could emerge from the relationships between quantum loops, like a movie stitched together frame by frame. This challenges everything from how we simulate the early universe to whether, before the Big Bang, even means anything. Yet for all its elegance, loop quantum gravity remains frustratingly hard to test. Unlike string theory, which posits extra dimensions and new particles, this framework sticks to the austere beauty of space and time alone, making it harder to confirm but also harder to disprove. It's a theory that demands patience, pushing us to rethink not just gravity, but the very nature of reality's building blocks. Now imagine if the universe's tiniest building blocks weren't dots or loops at all, but wriggling, vibrating strings. That's the bold premise of string theory, one of the most ambitious frameworks in the quest for quantum gravity. Instead of particles as zero-dimensional points, this theory suggests everything, from quarks to photons to the force of gravity itself, stems from infinitesimal strings, each vibrating at different frequencies like the strands of a cosmic guitar. Pluck one string and you get an electron. Pluck another and you might get a graviton, the hypothetical particle carrying gravity's force. String theory doesn't just tweak our understanding of matter, it demands a complete overhaul of reality's stage. To make the math work, the theory insists space-time isn't the four-dimensional fabric we're used to. It requires extra dimensions, possibly 10 or even 11, curled up so tightly we'd never notice them. Picture an ant walking along a telephone wire. From a distance, the wire looks one-dimensional, but up close, the ant senses the wire's full cylindrical shape. Similarly, these hidden dimensions could be compacted into complex shapes called Calabi-Yau manifolds, influencing how particles behave without ever revealing themselves directly. Where loop quantum gravity sticks to the gritty details of space-time itself, string theory aims higher. It's a theory of everything, attempting to unify all fundamental forces, gravity, electromagnetism, and the nuclear forces under one mathematical roof. That includes gravity's stubborn refusal to fit into quantum mechanics. By describing gravitons as closed-loop strings, the theory naturally incorporates them into the quantum world, sidestepping the infinities that plague other approaches. But string theory has its own complications. For starters, there isn't just one version, there are multiple variants like type I, type E, and heterotic strings, each with different symmetries and properties. Then there's M-theory, a grander framework proposing that all these string theories are facets of a single, deeper reality, where membranes and higher dimensional objects replace strings entirely. Critics argue that string theory's beauty is also its weakness. It's so flexible that it risks becoming untestable. Without a clear experimental signature, like a telltale particle or a twist in gravity's behavior, it's hard to prove or disprove. Yet supporters counter that its sheer mathematical elegance hints at truth, pointing to unexpected connections like the holographic principle, where a universe's information might be encoded on its boundary, much like a 3D hologram projected from a 2D surface. Whether string theory ultimately holds the key to quantum gravity or remains a dazzling intellectual detour, it's forced physicists to think bigger, literally. By rewriting the rules of dimensionality and matter, it challenges us to consider that the universe's deepest secrets might be hiding in geometries we can't yet see or even imagine. String theory may be elegant, but it's not without its skeptics. One of the loudest criticisms, after decades of research, it still hasn't produced a single testable prediction we can probe with experiments. In science, a theory isn't just a beautiful idea. It needs to make falsifiable claims, something string theory struggles with. The energy scales required to detect these tiny strings or uncurl those hidden dimensions are far beyond anything our particle colliders can reach. Even the Large Hadron Collider, smashing protons at nearly the speed of light, operates at energies billions of times too weak to glimpse strings directly. Without empirical evidence, some argue string theory veers closer to metaphysics than physics, a dazzling mathematical playground with no clear connection to reality. Then there's the infamous landscape problem. The math of string theory doesn't point to one unique universe but to a staggering number of possible solutions, perhaps 10 to the 500 versions of reality, each with different physical constants, particle types, even dimensions. This multiverse of possibilities raises a thorny question. If anything can happen somewhere in the string theory landscape, how do we explain why our universe has the precise rules that allow stars, planets, and life? Critics say this makes string theory untestable by default. If every possible outcome exists, the theory can't be proven wrong, and in science that's a fatal flaw. Supporters counter that we might one day find a mechanism like cosmic inflation that explains why our universe's parameters are special. But for now, the landscape feels less like a prediction and more like a retreat from prediction altogether. The debate splits the physics community. Nobel laureate Sheldon Glashow once compared string theorists to medieval theologians, crafting intricate arguments untethered from experiment. Others, like Brian Greene, argue that groundbreaking theories often outpace technology. General relativity sat untested for years before eclipses, and GPS confirmed it. String theory's defenders point to its mathematical feats, like solving black hole entropy puzzles or inspiring the holographic principle. They say it's too soon to dismiss a framework that's reshaped how we think about space, time, and quantum entanglement. So is string theory science. It depends on whom you ask. For some, it's a temporary bridge, a way to grapple with quantum gravity until something better emerges. For others, it's the only game in town daring enough to tackle the universe's deepest questions, even if the answers remain just out of reach. One thing's certain, whether it's ultimately right or wrong, string theory has already expanded the horizons of human imagination, pushing us to consider that reality might be far stranger and more beautiful than we ever dreamed. What if space-time isn't made of loops or strings but tiny, shimmering triangles? That's the striking vision of causal dynamical triangulations, a theory that slices reality into geometric chunks so small they rewrite the rules of gravity itself. Imagine taking the smooth fabric of space-time and pixelating it into a cosmic mosaic, where every tile is a microscopic triangle connecting to its neighbors in a precise causal sequence. This isn't just abstract math, it's a radical attempt to tame the chaos of quantum gravity by insisting that space-time doesn't just have structure, it has rules. Unlike loop quantum gravity's tangled webs of vibrating loops, this framework builds space-time from the ground up using simple, rigid shapes, specifically four-dimensional triangular blocks called simplices. Picture a geodesic dome, but instead of hexagons, every facet is a hyperdimensional triangle stitching together moments of time and space, the key innovation. These triangles don't just connect randomly, they obey strict cause and effect relationships. Every new triangle must follow from the ones before it, creating a lattice where time only flows forward, never backward or in disconnected jumps. This causal rule isn't just philosophical, it's the theory's secret weapon, filtering out the nonsensical geometries that plague other quantum gravity models. The result is a universe where space-time emerges from the collective behavior of these geometric building blocks, like a flipbook animation creating motion from still frames. At large scales, the jagged edges smooth out, recovering Einstein's classical space-time, but zoom in far enough, and you'd see reality's granular skeleton. This approach has a surprising advantage. It sidesteps the pathological solutions that haunt other theories, like wormholes tunneling randomly through time or universes that sprout infinite fractal branches. By enforcing causality at the smallest scales, the theory naturally avoids these cosmic paradoxes, but the real magic happens when you run the numbers. Simulate this triangulated universe on a supercomputer, and something remarkable occurs. The triangles self-organize into a four-dimensional structure without any prior assumption that space-time should have four dimensions. It's as if the theory rediscovers the familiar fabric of reality from scratch, hinting that causality and geometry might be deeper truths than we realized. Critics point out that the model relies on a fixed mathematical scaffolding, unlike loop quantum gravity's more flexible loops or string theories evolving strings. Yet supporters argue this rigidity is a feature, not a bug. It keeps the math clean and the physics testable. While no experiment has yet detected these space-time triangles, the theory offers a tantalizing possibility. If space-time is truly pixelated, subtle signatures might lurk in high-energy cosmic rays or the afterglow of the Big Bang waiting to be found. Whether causal dynamical triangulations ultimately hold the key to quantum gravity or not, they offer something profound. A vision of reality where even the flow of time itself emerges from something simpler, more elemental. It's a reminder that sometimes the universe's deepest truths hide in the humblest shapes, triangles, stacked one after another, writing the history of existence itself. Computer simulations of causal dynamical triangulations reveal something astonishing. The jagged, pixelated space-time at the smallest scales somehow smooths out into the familiar, continuous universe we experience. It's like watching a mosaic from a distance. Up close, you see individual tiles, but step back and the image blends into a seamless whole. Researchers running these simulations start with countless tiny triangular building blocks, each obeying strict causal rules, and let the system evolve. Over time, something magical happens. The chaos of quantum foam gives way to an ordered, four-dimensional space-time, all without forcing the outcome. The structure emerges from the math as if the universe itself is solving the puzzle of its own geometry. This emergent smoothness isn't just a mathematical trick, it's a clue to how quantum gravity might hide its granular nature from our everyday perception. Think of it like the pixels on your phone screen. Swipe your finger across it and the motion feels fluid, even though you're really interacting with discrete dots of light. Similarly, the Planck scale triangles in this theory are so unimaginably small that their rough edges vanish when averaged over larger scales, leaving behind the smooth curves of Einstein's relativity. But the theory's most tantalizing prediction is quantum foam, the idea that at the tiniest scales, space-time bubbles with fluctuations like a boiling pot of water. Simulations show these frothy, dynamic geometries where triangles briefly disconnect or reconfigure, creating fleeting wormholes or tunnels in space-time. It's a wild departure from classical physics, suggesting that empty space isn't empty at all, but a seething quantum ocean. The catch: this foam only appears at energies so high, we'd need a particle accelerator the size of a galaxy to probe it directly. So why hasn't this theory gained the same spotlight as string theory or loop quantum gravity? For one, it's computationally brutal. Simulating even a tiny patch of universe requires staggering processing power, limiting how far researchers can scale the model. Then there's the rigidity problem. The theory's strict causal rules, while elegant, might be too restrictive to capture the full chaos of quantum gravity. Critics argue reality at the Planck scale could be far messier, with geometries that don't neatly fit into tidy triangular grids. Yet for all its challenges, causal dynamical triangulations offer something rare: a concrete, visual approach to quantum gravity. Unlike abstract strings or tangled loops, this theory lets us see space-time being built triangle by triangle in simulations. It's a reminder that sometimes the universe's deepest truths aren't hidden in complex equations, but in the simple, timeless shapes that underpin reality itself. Now let's shift gears to a theory that takes a radically different approach to taming gravity's unruly quantum behavior: asymptotic safety. Picture this: what if gravity's wild infinities didn't arise because the theory was flawed, but simply because we've been measuring it wrong? That's the bold claim behind asymptotic safety, an idea first proposed by Nobel laureate Steven Weinberg in the 1970s. Unlike string theory's extra dimensions or loop quantum gravity's granular space-time, this framework suggests gravity might already be a perfectly consistent quantum theory if we just look at it the right way. The key lies in something called renormalization, a mathematical trick physicists use to sweep infinities under the rug in quantum field theory. Normally, gravity resists this fix. Its equations explode with infinities when you try to calculate particle interactions at tiny scales. But asymptotic safety flips the script. It proposes that at extremely high energies, gravity's strength, its so-called couplings, stop changing and settle into a fixed point, like a river smoothing out as it reaches the sea. At this critical point, the infinities cancel out naturally and gravity becomes predictable again. No new dimensions, no pixelated space-time, just gravity behaving itself when pushed to its limits. Recent advances in lattice calculations, where space-time is simulated as a discrete grid, have given this idea new life. Supercomputer models show hints that gravity's couplings might indeed flow toward such a fixed point, just as Weinberg predicted. It's as if gravity has a hidden safety switch, preventing it from spiraling into chaos at the quantum scale. But asymptotic safety isn't without its skeptics. Some argue the fixed point might be a mathematical mirage, an artifact of approximations rather than a real feature of nature. Others point out that even if the theory works, it doesn't answer why gravity chooses this particular fixed point, leaving a puzzle wrapped inside an enigma. Yet if true, the implications are profound. It would mean Einstein's general relativity isn't just an approximation, it's the low-energy shadow of a deeper, perfectly finite quantum theory. Black holes, the Big Bang, even the nature of dark energy could all look different through this lens. The universe's most mysterious force might not need rewriting after all, just a sharper set of tools to reveal its hidden order. The strongest hints for asymptotic safety come from lattice quantum chromodynamics, a computational technique that chops space-time into a fine grid to simulate quantum fields numerically. When researchers apply these methods to gravity, something curious emerges. The calculations suggest gravity's strength might indeed plateau at ultra-high energies, just as Weinberg predicted. Imagine stretching a rubber band to its limit. At first, it resists more the farther you pull, but there's a point where it can't stretch any further. Lattice simulations hint that gravity behaves similarly, reaching a fixed intensity where its quantum fluctuations finally stabilize, but not everyone's convinced. Skeptics argue that these lattice results could be artifacts of the simulation's artificial cutoffs, like mistaking the edge of a map for the edge of the world. Without direct experimental evidence, asymptotic safety risks becoming a self-fulfilling prophecy where the math is tweaked until it behaves. Compare this to other renormalization strategies like dimensional regularization in particle physics, where infinities are tamed by pretending space-time has fractional dimensions. That method works brilliantly for electromagnetism and the nuclear forces, but gravity stubbornly resists the same treatment. Asymptotic safety supporters counter that gravity might simply play by different rules. Its fixed point isn't a mathematical trick but a fundamental feature of nature, like the speed of light in relativity. Then there's the too good to be true critique. If gravity becomes finite and predictable at high energies, why hasn't nature given us clearer signs? Other quantum gravity proposals, like string theory, at least demand radical shifts in our understanding extra dimensions. Holographic universes, while asymptotic safety asks us to believe that Einstein's equations were almost perfect all along. To some, that feels suspiciously neat. Yet the theory's minimalist appeal is also its strength. Unlike frameworks that overhaul reality with unseen dimensions or pixelated space-time, asymptotic safety suggests the answers might lie hidden in gravity's own math, waiting to be decoded. Whether it's the final word on quantum gravity or just a stepping stone, one thing's certain: it's forcing physicists to ask whether the universe's deepest mysteries might be simpler than we dared imagine, or whether we're just seeing what we want to see. What if gravity isn't a fundamental force at all, but a side effect of the universe's hidden chaos? That's the startling premise of entropic gravity, a theory that turns our understanding of physics upside down. Proposed by physicist Eric Verland, this idea suggests gravity isn't some elemental force woven into space-time. It's an illusion, emerging from something far more subtle: the relentless drive of entropy, the universe's tendency toward disorder. Verland's theory builds on a groundbreaking connection between gravity and thermodynamics, the science of heat and energy. It started with black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of their hidden information, and even radiate heat, now called Hawking radiation. This was bizarre. How could a black hole, the ultimate vacuum cleaner of the cosmos, behave like a warm coal radiating energy? The answer hinted at something profound. Gravity and thermodynamics might be two sides of the same coin. Fast forward to 2010, when Verland took this idea further. He argued that gravity isn't a standalone force but an emergent phenomenon, like how the pressure of a gas emerges from countless random collisions of molecules. In this view, gravity arises from the universe's quantum microstates, the myriad ways information can be scrambled at the tiniest scales. When masses interact, they're not pulling on each other through some invisible field. They're effectively responding to shifts in this underlying information landscape. Here's where it gets wild. Entropic gravity ties into the holographic principle, the idea that our three-dimensional universe might be a projection of information encoded on a two-dimensional surface, like a cosmic Instagram post. Just as a hologram stores 3D data on a flat sheet, space-time structure, and gravity with it could be a kind of thermodynamic mirage. This would mean the force keeping planets in orbit or apples falling from trees isn't fundamental at all. It's a byproduct of the universe's deep informational architecture. But can this theory hold up to reality? Verland's math reproduces Newton's laws and even tweaks Einstein's relativity in ways that might explain dark matter without invoking invisible particles. If correct, galaxies' rotation curves, which currently require dark matter's gravitational tug, could instead stem from entropy gradients in space-time itself. Some astronomers are testing this by studying galaxy clusters for deviations from Einstein's predictions, though results remain inconclusive. Critics argue entropic gravity lacks the precision of traditional quantum gravity frameworks, and its predictions often blur into metaphysics. Yet supporters counter that it's a paradigm shift, one that reframes gravity not as a force, but as a cosmic game of statistics, where the real action happens in the fine print of reality's code. Whether Verland's vision survives or not, it's a reminder that sometimes the universe's deepest truths hide in the last place we'd think to look, not in the forces we measure, but in the information we've yet to decode. Entropic gravity challenges everything we thought we knew about the cosmos, but not everyone's convinced. One of the biggest criticisms, the theory struggles to account for galaxy rotation curves without sneaking dark matter back into the equation. Here's the problem: stars at the edges of spiral galaxies orbit so fast that, according to Newton's laws, they should fling off into space. Dark matter solves this by adding invisible mass, but Verland's theory claims its unnecessary gravity itself behaves differently due to entropy gradients. Yet when physicists crunch the numbers, entropic gravity often falls short, matching observations only if you tweak it with extra assumptions. Critics argue this makes it just a fancier way to hide dark matter under another name. Then there's the question of scale. Thermodynamics works beautifully for systems in equilibrium, like steam engines or black holes. But gravity operates everywhere, from colliding neutron stars to the whisper-thin voids between galaxies. Can entropy really explain the precise pull of a falling apple and the bending of light around galaxy clusters? Skeptics point out that Verland's math relies heavily on holographic principles, which themselves remain unproven. It's like building a house on a foundation of maybe intriguing but shaky. But the loudest critique might be philosophical. Is entropic gravity revolutionary or just rearranging the deck chairs? Traditional quantum gravity theories aim to quantize space-time, treating it as something to be broken into pieces. Entropic gravity flips the script, suggesting gravity isn't fundamental at all. To supporters, this is a Copernican-level shift, dethroning gravity from its place among the fundamental forces. To detractors, it's a sleight of hand, a poetic metaphor that doesn't actually solve the quantum gravity problem. Yet, even amid the backlash, entropic gravity sparks vital questions. Why do gravity and thermodynamics seem so deeply linked? Could there be a kernel of truth here, waiting for a more refined theory to unlock it? The debate isn't just about equations, it's about how we frame reality itself. Whether Verland's vision fizzles or flourishes, it's already done something remarkable, forced physicists to ask if gravity's secret isn't in the fabric of space, but in the chaos hiding beneath it. Imagine if the fabric of reality wasn't made of loops, strings, or triangles, but simple, indivisible points connected by pure cause and effect. This is the radical simplicity of causal set theory, where space-time isn't a smooth continuum or a pixelated grid, but a vast network of moments linked by an unbreakable chain of causality. Each point in this cosmic web represents a tiny event, and the connections between them, like arrows of influence, dictate how reality unfolds. There's no pre-existing geometry, no background stage, just these raw causal relationships building space and time from the ground up. The elegance lies in the minimalism. Unlike other quantum gravity approaches that start with complex mathematical structures, causal sets strip everything down to two basic ingredients: discrete points and the order in which they influence one another. Picture a cosmic game of dominoes where each tile's fall triggers the next, creating a cascade that becomes the flow of time itself. There's no need to assume space-time exists beforehand. It emerges naturally from the pattern of connections, like a melody arising from individual notes. This approach solves one of quantum gravity's thorniest problems: how to reconcile the smooth, curved space-time of Einstein's relativity with the choppy, quantum nature of reality at microscopic scales. In causal sets, the smoothness we perceive is a kind of illusion, a statistical averaging of countless discrete points, much like a movie appears continuous despite being made of separate frames. The theory even suggests a natural resolution to the Big Bang singularity. With no pre-existing time, there's no first moment, just an unbroken chain of causes stretching backward indefinitely. Yet for all its conceptual beauty, causal set theory faces a steep challenge: how to recover the familiar four-dimensional universe from this sparse network of points. The equations allow for universes with too many dimensions or where time behaves unpredictably, scenarios that don't match our reality. Researchers tackle this by introducing dynamical rules that favor certain causal structures over others, pruning the mathematical weeds until only plausible spacetimes remain. It's a bit like teaching a child to connect dots in a way that eventually reveals a coherent picture, not a scribble. Another hurdle is the trade-off between discreteness and locality. In relativity, events close in space-time are causally linked, but in causal sets, close loses its usual meaning. Points can influence each other in ways that defy classical geometry. Some theorists argue this could explain quantum entanglement's spooky action at a distance, where particles instantly affect each other across vast spans. Others worry it might make the theory untestable, blurring the line between prediction and speculation. Still, causal sets offer something rare, a theory where time isn't just real but fundamental. While other frameworks struggle to explain why time flows irreversibly, here it's baked into the architecture. Each causal link points forward, never backward. This could revolutionize everything from black hole physics to the arrow of time itself. Whether causal sets ultimately unlock quantum gravity or remain a provocative thought experiment, they remind us that sometimes the simplest ingredients, points and connections, can give rise to the universe's grandest complexities. No loops, no strings, no extra dimensions, just the raw causal skeleton of reality, waiting to be uncovered. Einstein's relativity hinges on a sacred principle: Lorentz invariance, the idea that the laws of physics stay the same no matter how fast or in what direction you're moving. It's why time slows down for an astronaut racing near light speed, or why a muon created in the upper atmosphere can reach Earth's surface despite its fleeting lifespan. But here's the catch: when you chop space-time into discrete pieces like the causal sets we just discussed, this symmetry shatters like glass. If reality has a smallest possible chunk, wouldn't that create a preferred direction or frame of reference, violating relativity's core tenet? It's a paradox that's derailed countless quantum gravity theories, but causal sets might have an ingenious workaround: sprinkling. Instead of forcing space-time into a rigid grid, imagine scattering points randomly across the cosmos like seeds tossed onto soil. Each seed represents an event, and the connections between them, which came before, which naturally build the fabric of causality. This stochastic approach, inspired by mathematician Raphael Sorkin, preserves Lorentz invariance statistically. While individual points might look jagged and uneven up close, zoom out far enough, and the distribution smooths into the seamless, symmetric space-time relativity demands. It's like the static on an old TV: random noise at a glance, but average it over time, and you get a coherent picture. The magic lies in the math. By using a Poisson distribution, a tool from probability theory that models rare, independent events, the sprinkling ensures no region of space-time is ever truly special. Just as raindrops fall unpredictably yet evenly drench a sidewalk, causal points distribute in a way that hides their discreteness from any observer, no matter their motion. This statistical camouflage is key. Unlike a lattice where edges and corners would break relativity's symmetry, a sprinkled causal set has no preferred axes or directions. Move through it at any speed, and the universe looks the same, but the solution isn't perfect. Critics argue that while sprinkling saves Lorentz invariance in principle, it's unclear how the theory recovers precise relativistic effects like time dilation or length contraction from this fuzzy foundation. Others worry that quantum effects at the Planck scale could amplify the randomness, leading to observable deviations from Einstein's predictions, something we've yet to detect. Despite the challenges, causal sets offer something profound, a glimpse of how relativity's elegance might survive the quantum fray. It suggests that the universe's deepest symmetries aren't etched into its building blocks but emerge from their chaos like order rising from a storm. And that's a lesson worth remembering sometimes. The most perfect symmetries aren't imposed from above, but woven from below, one random thread at a time. What if space-time itself had a built-in fuzziness, not just at the quantum level, but in its very coordinates? That's the mind-bending premise of non-commutative geometry, a theory suggesting that at the tiniest scales, the familiar rules of location break down in a way that would make even Heisenberg's uncertainty principle blush. In our everyday world, coordinates commute, meaning if you move 5 meters east and then 3 meters north, you end up in the same spot as if you'd moved 3 meters north first, then 5 meters east. But in this framework, that simple logic crumbles. Space-time's coordinates might refuse to commute, implying that order matters at the Planck scale. Swapping measurements of position could yield different results, as if reality itself has a quantum-level stubbornness about where things truly are. This isn't just abstract speculation, it's rooted in the work of mathematician Elaine Connes, who reshaped geometry by treating space as a mathematical construct where points aren't fixed markers but more like overlapping possibilities. Think of it like trying to pinpoint the exact edge of a cloud. The closer you look, the fuzzier it becomes. In non-commutative geometry, space-time isn't a static grid but a dynamic, almost musical structure where coordinates behave like operators in quantum mechanics, refusing to settle into neat classical values. The implications are staggering. If position and time become non-commutative, the very notion of distance blurs at microscopic scales. Two events could appear separated by one measurement but overlap in another, challenging our ideas of locality, the principle that objects need direct contact or an intermediary force to influence each other. This could explain quantum entanglement's spooky action at a distance, where particles seem to coordinate instantly across vast gaps. If space-time's coordinates are inherently uncertain, perhaps distance isn't as fundamental as we thought. Connes' framework also offers a fresh path to unifying gravity with quantum mechanics. By reimagining space-time as an algebraic structure rather than a smooth continuum, the theory sidesteps the infinities that plague traditional quantum field theories. Gravity, in this view, emerges from the algebra's spectral properties, a bit like how the pitch of a musical note arises from the vibrations of a string. The equations even hint at a deep link between the Higgs boson and gravity, suggesting the two might be facets of the same geometric tapestry. Yet non-commutative geometry isn't without its critics. Some argue it's too abstract, divorcing physics from intuitive spacetime pictures. Others note that while the math is elegant, testable predictions remain elusive. Would this fuzziness leave traces in high-energy particle collisions or gravitational waves? So far, no experiment has spotted definitive signs, but the theory's proponents counter that we might just need sharper tools. What makes this idea so compelling is its audacity. It doesn't just tweak Einstein's relativity or quantize gravity, it redefines the stage itself. If Connes is right, the universe isn't built on a rigid scaffold of points and lines, but on a shimmering, non-commutative symphony where space and time dance to a quantum tune we're only beginning to hear. Non-commutative geometry doesn't just tweak our understanding of tiny scales, it could rewrite the story of the universe's birth. If space-time's coordinates behave like quantum operators at the Planck scale, the early cosmos might have been a place where directions blurred and distances flickered unpredictably. Picture the Big Bang not as a singular explosion in a smooth void, but as a seething geometric storm where here and there lost all meaning. In this chaos, the theory suggests inflation. The universe's rapid exponential expansion might not have been driven by a hypothetical inflattened field, but by the spacetime foam's inherent non-commutativity. The algebra itself could have generated repulsive gravity, acting as a cosmic accelerator without needing additional particles or fields. Dark energy, the mysterious force pushing the universe apart today, might also find an elegant explanation here. If the non-commutative nature of space-time leaves a residual fuzziness even at large scales, it could mimic the effects of a cosmological constant, Einstein's greatest blunder turned modern enigma. The math hints that what we call dark energy might just be the ghostly imprint of quantum geometry's refusal to settle into classical certainty. It's as if the universe's expansion isn't fueled by some exotic energy, but by the lingering turbulence of its earliest, most anarchic moments. Yet for all its conceptual brilliance, the theory faces a daunting hurdle. Its abstract math resists translation into testable predictions. Unlike string theories, gravitons, or loop quantum gravity's pixelated space-time, non-commutative geometry deals in spectral triples and operator algebras, tools more familiar to mathematicians than experimentalists. How do you design a telescope or particle detector to measure the non-commutativity parameter of space-time? Current proposals look for subtle anomalies in high-energy cosmic rays or distortions in the cosmic microwave background, but these signals would be extraordinarily faint, buried under noise and competing effects. Some theorists argue this isn't a flaw but a reflection of reality's deepest layers. Perhaps the quantum gravity regime is simply too far removed from our experimental reach. Others counter that a theory without observable consequences strays dangerously close to metaphysics. The tension lies at the heart of modern physics, between the allure of mathematical beauty and the insistence on empirical grounding. What makes non-commutative geometry so compelling, despite the challenges, is its audacious reimagining of reality's scaffolding. It doesn't just add quantum frosting to Einstein's cake, it bakes an entirely new dessert, one where space, time, and even the concept of where dissolve into a deeper, more fundamental algebra. Whether this vision ultimately aligns with nature or remains a stunning intellectual artifact, it reminds us that the universe's secrets might not live in the equations we've mastered, but in the math we've yet to invent. What if gravity isn't a fundamental force, but something that bubbles up from the quantum chaos beneath reality, like sound waves emerging from the vibrations of atoms in a crystal? This is the provocative idea behind emergent gravity, a theory suggesting that what we feel as gravity might just be a side effect of deeper, more intricate physics playing out at the smallest scales. Think of it like the way phonons, collective vibrations in a solid, give rise to the phenomenon of sound, even though no single atom is making noise on its own. In this view, gravity could be a kind of cosmic phonon, a ripple in the fabric of quantum information that only looks like a force when we zoom out. One of the key architects of this idea is Nobel laureate Gerard T. Hooft, who drew parallels between gravity and condensed matter systems like superconductors or superfluids, where collective behavior creates entirely new phenomena. In a superconductor, for instance, electrons pair up and move in lockstep, giving rise to zero resistance, a property none of the individual particles possess alone. Similarly, T. Hooft proposed that space-time itself could be a kind of quantum condensate, with gravity emerging from the way microscopic degrees of freedom organize on vast scales. It's as if the universe is a grand orchestra and gravity is the symphony we hear, unaware of the individual musicians playing their parts. The theory takes inspiration from an unexpected place: black hole thermodynamics. Just as a black hole's entropy, a measure of its hidden information, is proportional to its surface area rather than its volume, Emergent gravity suggests that the information encoding gravity might live on a lower dimensional boundary, not in the bulk of space. This holographic flavor ties into T. Hooft's earlier work, where he showed that certain quantum systems could be described entirely by their boundary conditions with no need to reference the interior. If gravity follows the same rules, it would mean we've been looking for it in the wrong place all along, not as a force within space, but as a shadow cast by quantum interactions at its edges. Critics argue that emergent gravity struggles to explain why Einstein's equations work so flawlessly in our everyday universe if they're just an approximation. How does the smooth, geometric language of general relativity emerge from something as abstract as quantum information? Supporters counter that this is precisely what makes the theory powerful. It doesn't discard Einstein's insights but reinterprets them as part of a larger, more nuanced picture. Just as thermodynamics doesn't negate Newton's laws but explains them in terms of atomic motion, emergent gravity could be the missing link between quantum mechanics and the cosmos we observe. Yet the theory's biggest hurdle is experimental. If gravity is emergent, where are the telltale deviations from classical predictions? Some models suggest subtle anomalies might appear in extreme environments like near the event horizon of a black hole or in the primordial universe where quantum effects would peek through the veil. Others speculate that dark matter's mysterious influence could actually be a signature of gravity's emergent nature, with galactic rotation curves reflecting the underlying quantum soup rather than invisible particles. Whether emergent gravity ultimately holds the key to uniting quantum mechanics and relativity, or becomes a stepping stone to something even stranger, it's a reminder that sometimes the universe's most familiar forces are just the tip of an iceberg, a shadow of deeper, wilder rules we're only beginning to decode. Emergent gravity finds one of its most compelling frameworks in a concept so radical it seems ripped from science fiction: the holographic principle. At its core, this idea suggests our three-dimensional universe, complete with its gravitational forces, might actually be a projection of information encoded on a two-dimensional surface at its boundary. Think of it like a cosmic credit card hologram. The embossed bird that appears to hover above the card isn't really there. It's a 3D illusion generated by microscopic patterns etched into the flat surface. Similarly, the AD-S/CFT correspondence, a specific realization of holography proposed by physicist Juan Maldacena, posits that gravity in a higher dimensional space can be entirely described by a lower dimensional quantum field theory without gravity at all. This connection between anti-de Sitter space AD-S, a type of curved universe with a negative cosmological constant, and conformal field theory CFT, a quantum framework that lives on its boundary, is more than just mathematical sleight of hand. It implies that the force we experience as gravity isn't fundamental but encoded in the interactions of quantum particles living on the universe's edge. For example, a black hole in the 3D bulk of space would correspond to a specific thermal state of the 2D quantum system, meaning all the mysteries of black hole thermodynamics, from entropy to Hawking radiation, could be translated into the language of particles and fields on the boundary. It's as if the universe is running a cosmic simulation with gravity as the rendered output. The implications are staggering. If true, AD-S/CFT could resolve long-standing paradoxes like the black hole information problem by showing that information swallowed by a singularity isn't lost, it's just stored on the boundary in a scrambled quantum state. It also offers a concrete mechanism for emergent gravity. The collective behavior of quantum fields on the boundary generates the curvature of space-time in the bulk. Much like the synchronized motion of audience members in a stadium can create a wave that wasn't present in any individual. But there's a catch. While AD-S/CFT is mathematically elegant, our universe isn't an anti-de Sitter space. It's expanding at an accelerating rate, better described by de Sitter geometry. Translating the holographic principle to our real cosmos remains an open challenge. like trying to adapt a brilliant recipe written for one type of oven to another that behaves completely differently. Some theorists are exploring DS/CFT variants, where the boundary theory might live in the infinite future, but the math becomes fiendishly complex. Testing these ideas is even thornier. The holographic principle operates at energy scales so extreme that direct observation is impossible with current technology. Instead, researchers hunt for indirect signatures, like anomalies in quantum entanglement patterns or unexpected symmetries in particle collisions, that might hint at a hidden boundary description. Others simulate toy models using quantum computers, probing whether simplified holographic systems really do reproduce gravitational phenomena. Yet, even unproven, the AD/CFT correspondence has already reshaped theoretical physics. It's revealed profound links between entanglement and space-time geometry, suggesting that the very fabric of reality might be woven from quantum connections. Whether it's the final word on gravity or just a stepping stone, one thing's clear: the universe's deepest truths might not live in the dimensions we see, but in the hidden codes written at its edges. What if the key to taming gravity's quantum chaos isn't adding extra dimensions or pixelating space-time, but tweaking the very symmetry that defines reality? Enter Holographic Gravity, a radical theory that tackles renormalization head-on by breaking one of physics' most sacred rules, Lorentz symmetry. In most quantum gravity approaches, maintaining this symmetry, the idea that the laws of physics stay identical for all observers moving at constant speeds, is non-negotiable. But Peter Holographic dared to ask, what if Lorentz symmetry only emerges at low energies, like the smooth surface of a frozen lake that cracks under extreme pressure? The theory's genius lies in its asymmetry. At high energies approaching the Planck scale, Holographic proposed that space and time stop behaving as equals time gets sticky, flowing differently than space's 3 dimensions. Picture a block of rubber being stretched. Normally, it deforms equally in all directions, but what if the vertical direction resisted stretching more than the horizontal? Similarly, in Holographic Gravity, time's behavior becomes distinct, introducing a preferred cosmic clock that governs quantum fluctuations. This temporal rigidity gives gravity a lifeline. The theory's equations become renormalizable, meaning those pesky infinities plaguing traditional quantum gravity calculations finally cancel out. Cosmologists love this framework because it offers fresh solutions to the early universe's thorniest puzzles. Inflation, that brief period of exponential expansion moments after the Big Bang, usually requires an ad hoc inflattened field to drive it. But in Holographic Gravity, the asymmetry between time and space naturally generates repulsive gravity at high energies, potentially powering inflation without exotic particles. The theory also suggests an alternative to the singularity problem. The early universe might have experienced a bounce rather than a true singularity, with the modified time dynamics preventing infinite densities. Black holes get a makeover too. Their event horizons could develop exotic structures where time grinds to a halt more dramatically than in Einstein's relativity phenomena that might leave imprints in gravitational wave signals. Some models even predict that black holes older than the universe itself could exist, relics from a pre-Big Bang phase where Holographic Gravity dominated. Yet the theory isn't without controversy. Breaking Lorentz symmetry is heresy to many physicists after all. Relativity's core principle has survived over a century of brutal testing. Critics argue that even tiny Lorentz violations should have been spotted in particle collisions or cosmic ray observations by now. Others worry the theory's preferred time direction clashes with quantum mechanics' time-symmetric foundations. But Holographic Gravity's boldness is also its strength. By questioning sacred symmetries, it forces us to confront whether our deepest assumptions about space and time might just be low-energy approximations, like Newton's laws before Einstein. Whether the theory ultimately holds up or inspires something even stranger, it reminds us that sometimes progress demands breaking a few symmetries to see what lies beyond. Holographic gravity's elegant solution to renormalization comes at a cost. The theory depends on razor-thin, fine-tuning to match the universe we observe. Like a watchmaker adjusting tiny gears to perfection, the framework requires its critical exponent, a parameter dictating how strongly time resists stretching compared to space, to be dialed to an exact value for the math to produce familiar physics. Deviate even slightly, and suddenly black holes evaporate too quickly, or cosmic expansion veers wildly off course from what astronomers measure. This sensitivity raises eyebrows because natural systems rarely balance on such a knife's edge without deeper mechanisms at play. The tension becomes stark when confronted with neutron star mergers, cosmic collisions that serve as gravity's ultimate stress tests. During the infamous 2017 event GW 170817, where two neutron stars spiraled together, their gravitational waves and gamma-ray bursts arrived within seconds of each other after traveling over 100 million light-years. According to relativity, gravity and light should race through space-time at identical speeds, a prediction verified with astonishing precision. But Holographic gravity's broken Lorentz symmetry could introduce delays between the signals unless its parameters are precisely tuned to suppress these deviations. Critics argue this tuning feels suspiciously convenient, as if the theory is retrofitting itself to avoid falsification rather than making bold, testable claims. Worse, some versions of the theory struggle to explain why neutron stars don't implode under their own gravity. Einstein's equations predict these ultra-dense remnants balance gravity's crush against quantum repulsion between neutrons. But in Holographic models with generic parameters, the equations sometimes spit out nonsensical solutions, neutron stars that are either impossibly massive or collapse into black holes at lower densities than observed. To match reality, theorists must meticulously adjust the equations, threading a needle between mathematical consistency and observational truth. Skeptics liken this to forcing a square peg into a round hole. The more you shave the peg to fit, the less it resembles the original theory's promise. Defenders counter that all cutting-edge theories face tuning challenges early in their development. Even the standard model of particle physics relies on seemingly arbitrary numbers like the Higgs boson's mass that future theories might explain. The difference, opponents retort, is that the standard model's parameters are measured directly from experiments, while Holographic fine-tuning often feels like guesswork to dodge observational bullets. The debate cuts to the heart of scientific epistemology. Is a theory still elegant if its beauty depends on fragile numerical coincidences? Or might these precise values hint at undiscovered principles, a cosmic symmetry or selection effect waiting to be uncovered? Until gravitational wave observatories or neutron star studies uncover definitive deviations from relativity, Holographic gravity remains in limbo, a daring idea that could either revolutionize physics or serve as a cautionary tale about the allure of mathematical shortcuts. What if the true language of the universe isn't space, time, or particles, but shimmering geometric threads weaving reality together? That's the visionary premise of twistor theory, a radical framework where the familiar four-dimensional stage of existence takes a backseat to something far more elegant: twistors. Conceived by physicist and mathematician Roger Penrose in the 1960s, this approach flips conventional physics on its head. Instead of building reality from points in space-time, twistors treat space-time as a derivative, a secondary phenomenon emerging from a deeper, more fundamental structure. Imagine trying to understand a rainbow by studying individual water droplets rather than light itself. Twistor theory suggests we've been focusing on the droplets all along. At its core, a twistor is a complex geometric object encoding not just position and momentum, like traditional physics, but also the very relationship between a particle and the light it emits. Picture a strand of cosmic DNA where each twister carries information about both where a particle is and how it's moving through space-time. The magic happens when these twisters interact. Their intersections and tangles generate the fabric of space-time itself, much like how threads in a tapestry create an image when woven together. This perspective isn't just mathematically beautiful, it simplifies problems that stump conventional methods, particularly particle scattering. Calculations that require pages of algebra in quantum field theory collapse into elegant geometric constructions in the twister universe. Yet for all its grace, twister theory stumbles where gravity flexes its muscles. While it handles linear phenomena like massless particles zipping through flat space, with breathtaking efficiency, gravity's nonlinearity is a tougher nut to crack. In Einstein's relativity, mass warps space-time, which in turn tells mass how to move, creating a feedback loop that twisters struggle to encode naturally. Penrose himself likened the challenge to trying to build a cathedral with spaghetti. The delicate mathematical strands of twister geometry buckle under the weight of strong gravitational fields. Recent advances, however, hint at possible breakthroughs. By integrating ideas from quantum field theory and holography, researchers have extended twister methods to certain curved spacetimes like those near black holes. Some even speculate that twisters could bridge general relativity and quantum mechanics by revealing hidden symmetries in gravitational waves or cosmic singularities. But critics argue the theory remains more of a beautiful toolkit than a complete quantum gravity framework. Its power to simplify calculations doesn't yet equate to a full rewrite of physics rulebook. What makes twister theory irresistible isn't just its potential to solve problems, it's the way it reshapes how we see reality. By trading coordinates for geometry, it offers a glimpse of a universe where space and time aren't the foundation but the embroidery, stitched together by deeper, more luminous threads. Whether those threads ultimately weave into a theory of everything or remain a sublime mathematical curiosity, they remind us that sometimes the universe's secrets hide not in the equations we know, but in the geometry we've yet to discover. Twister theory's mathematical elegance has found surprising new life in one of physics' thorniest problems, calculating particle scattering amplitudes in quantum gravity. When particles collide at unimaginable energies, predicting how they ricochet traditionally involves monstrous equations drowning in infinite terms. But twisters slice through this computational nightmare with geometric grace. By translating particle interactions into intricate contour integrals on twister space, a kind of abstract cosmic sketchpad, physicists like Andrew Hodges and Nima Arconi have tamed calculations that once chewed through supercomputers. The amplituhedron, a jewel-like geometric object derived from twister-inspired methods, distills these chaotic quantum probabilities into starkly beautiful formulas, stripping away redundant mathematical baggage. It's like swapping a tangled ball of yarn for a pristine origami sculpture, the same information, but revealed in startling clarity. This computational prowess has drawn unexpected alliances with string theory. While twisters emerged from Penrose's quest to quantize space-time itself, string theorists now exploit their power to solve amplitudes in supersymmetric models, theoretical playgrounds where extra dimensions and partner particles simplify the math. The collaboration is symbiotic. Twisters offer string theorists sleek shortcuts through thickets of Feynman diagrams, while string theory provides twisters with a richer algebraic toolkit to handle curved backgrounds. Some researchers even speculate that twisters might be the missing link between string theory's higher dimensional brains and our four-dimensional perception of reality, a geometric Rosetta Stone waiting to be fully deciphered. Yet the theory's role remains hotly debated. Is it merely a revolutionary calculator, a GPS for navigating quantum gravity's chaotic equations, or does it hint at a deeper framework waiting to be uncovered? Skeptics point out that twistors still struggle to incorporate mass and strong gravity without ad hoc fixes, leaving Einstein's full theory only partially captured. The amplituhedron, for all its beauty, works flawlessly only in simplified toy universes without the messy complications of real-world particles. Supporters counter that every groundbreaking theory starts as a tool. Quantum mechanics itself began as a pragmatic fix for atomic spectra before revealing nature's probabilistic core. Recent work on celestial holography adds fuel to the debate. By projecting quantum field theory data onto a twistor-based boundary at infinity, a cosmic version of a movie projector's screen, physicists like Sabrina Pasterski have reconstructed space-time events purely from twistor correlations. This suggests twistors might not just describe reality but fundamentally encode it, like a cosmic QR stitched into the fabric of the sky. Whether twistor theory ultimately unmasks quantum gravity's secrets or remains a dazzling computational ally, its journey epitomizes theoretical physics at its best, a dance between abstract beauty and raw problem-solving, where even failed frameworks can illuminate paths no one thought to walk. Now imagine a theory that takes the granularity of loop quantum gravity and infuses it with the mathematical power of quantum field theory. That's the essence of group field theory. If loop quantum gravity describes space-time as a network of woven loops, this framework zooms in even further, proposing that those loops are themselves built from something more fundamental, tiny, abstract atoms of space that interact like particles in a quantum field. Think of it as a cosmic Lego set, where each brick isn't just a static piece but a dynamic entity vibrating with quantum potential, waiting to snap together with others to build the universe. The theory's backbone lies in its treatment of these space atoms as excitations in a field, not a field spread across space like the electromagnetic field, but one where the field itself creates space through its interactions. Picture a bustling marketplace where every transaction between vendors doesn't just exchange goods, but generates the very stalls and aisles of the market itself. Mathematically, this plays out using tools from group theory, where each atom carries labels related to symmetry groups, geometric transformations that dictate how it can connect to its neighbors. These connections form intricate networks reminiscent of tensor networks, a structure borrowed from quantum information theory that describes how entanglement correlations can be efficiently encoded. What makes group field theory particularly compelling is its versatility. Unlike some quantum gravity approaches that struggle to recover smooth space-time at large scales, this framework naturally bridges the granular and the continuous. When the interactions of these space atoms reach a critical density, they undergo a phase transition like water, freezing into ice, spontaneously giving rise to the familiar four-dimensional fabric of general relativity. It's as if the theory has a built-in smoothing mechanism, ensuring that the quantum chaos at microscopic scales doesn't disrupt the cosmic order we observe. The links to tensor networks are more than just analogy, they're a potential Rosetta Stone for quantum gravity. In quantum computing, tensor networks simplify the description of entangled states by focusing on local connections rather than global complexity. Similarly, group field theory suggests that space-time's structure might be written in the language of entanglement, with each atom of space contributing a node to a vast, evolving network. This perspective has even led to collaborations with condensed matter physicists, who see parallels between space-time's emergence and phenomena like topological order in exotic materials. Yet challenges remain. While the theory beautifully reconstructs classical geometry in certain limits, its full quantum dynamics are notoriously hard to solve, like trying to predict the exact pattern of a kaleidoscope by studying a single mirrored fragment. Some formulations also struggle to incorporate matter fields seamlessly, leaving open questions about how particles like electrons or photons fit into this geometric tapestry. But the promise is undeniable. By merging the discreteness of loop quantum gravity with the flexibility of field theory, group field theory offers a third way, one where space isn't just quantized but alive, built from humming quantum processes that weave reality moment by moment. Whether it's the final answer or just a stepping stone, it's a reminder that the universe's deepest layers might not be static or solitary, but vibrant, communal, and forever in dialogue. Group field theory doesn't just reshape our understanding of space, it rewrites the story of the cosmos itself. One of its most breathtaking revelations is the possibility of a universe without a true beginning, where the Big Bang wasn't a singular explosion from nothing but a dramatic turning point in an endless cosmic cycle. Picture a roller coaster cresting its highest peak. For a fleeting moment it pauses, suspended between ascent and descent. In this framework, the universe might operate similarly, with quantum corrections preventing the collapse into a singularity, and instead triggering a rebound, a quantum bounce, that births a new cosmic epoch from the ashes of the old. This bounce scenario isn't just poetic speculation, it's a mathematical lifeline for cosmology. Traditional general relativity predicts that the universe began as an infinitely dense, infinitely hot singularity, a point where the laws of physics break down entirely. But group field theory's granular space-time offers an escape hatch. When the universe contracts to near the Planck scale, the discrete nature of space-time resists further squeezing, like a spring compressed to its limit. Quantum geometry generates a repulsive force, halting collapse and sparking expansion anew. The result, a cyclic universe where each Big Bang is really a big bounce, eternally recycling matter and energy without ever hitting true nothingness. The parallels with loop quantum cosmology are striking. Both theories replace the singularity with a quantum bridge, a cosmic wormhole linking contraction to expansion. But while loop quantum gravity focuses on woven loops of space, group field theory's strength lies in its particle-like atoms of space and their collective behavior. Imagine comparing two symphonies, one where the music emerges from the interplay of individual instruments, and another where it arises from the resonance of the whole itself. Both describe harmonies, but their mechanisms differ profoundly. Observational clues might one day test these ideas. If the universe truly bounced, subtle imprints could linger in the cosmic microwave background, anisotropies in temperature or polarization patterns that defy standard inflation models. Some theorists even speculate that gravitational waves from the pre-bounce phase might survive, carrying whispers of a previous cosmic cycle. Detecting such signals would require telescopes of unprecedented sensitivity, but the payoff would be staggering, proof that our universe is but one page in an infinite cosmic novel. Yet the theory's grandeur comes with unresolved questions. What drives the cycles? Could entropy accumulate over eons, subtly altering each iteration until the universe no longer bounces? And if space-time is truly reborn in each cycle, does information from past universes persist, or is it erased like a chalkboard between lectures? These puzzles don't undermine the framework, they reveal its richness, inviting us to ponder whether time itself might be an emergent rhythm in a deeper, timeless dance. Whether group field theory's bounce scenarios ultimately describe reality or inspire better models, they offer something invaluable. A vision of the cosmos where endings are beginnings, and where the universe's most cataclysmic moment becomes a transformation, not a termination. It's a reminder that even in theoretical physics, the most profound revolutions often come full circle. Black holes aren't just cosmic vacuum cleaners, they're laboratories for quantum gravity, and their thermodynamics hold startling clues about how space and time might fracture at the smallest scales. Picture a star collapsing into oblivion, squeezing itself into a singularity where gravity becomes infinite. At that moment, something bizarre happens. The black hole's surface area, its event horizon, becomes a measure of its entropy, its hidden disorder. This was Jacob Bekenstein's revolutionary insight in the 1970s that black holes don't just trap matter, they encode information in the most counterintuitive way possible. Unlike ordinary objects where entropy scales with volume, a black hole's entropy is proportional to its surface area, as if all the information about what fell inside got smeared onto its boundary like cosmic graffiti. Then came Stephen Hawking's bombshell: black holes aren't truly black, they glow, radiating heat like a dying ember. This Hawking radiation emerges from quantum fluctuations near the event horizon, where particle-antiparticle pairs pop into existence. Normally, they annihilate instantly, but if one falls into the black hole while the other escapes, the whole loses energy and mass, slowly evaporating. Here's the twist: Hawking's math suggested the radiation was purely thermal, carrying no information about the black hole's contents. If a black hole fully evaporated, everything it swallowed, galaxies, planets, libraries, would vanish forever, leaving only generic heat behind. That violated quantum mechanics' sacred rule: information can't be destroyed. This information paradox became a battleground for quantum gravity. If Hawking was right, quantum theory needed rewriting. If not, general relativity had to bend. The debate raged for decades until string theorists made a breakthrough. Black holes might scramble and re-radiate information, like a cosmic hard drive burning data to a holographic backup. The AD/CFT correspondence suggested that information inside a black hole could be perfectly mirrored in quantum states on its horizon, gravity's version of a 2-for-1 deal. Yet mysteries linger. How does the information escape? Does it leak slowly, encoded in subtle correlations in Hawking radiation, or burst out in a final explosion? Recent island conjectures in holography propose that patches of the black hole interior, these so-called islands, might secretly belong to the exterior quantum system, acting as relays for information retrieval. It's as if the universe rigged the game to preserve its own rules. The stakes couldn't be higher. Black hole thermodynamics isn't just about dying stars, it's a Rosetta Stone for spacetime itself. The way entropy, temperature, and quantum mechanics collide at the event horizon might hold the key to unifying gravity with the quantum world. Every photon of Hawking radiation whispers a secret about reality's deepest structure if we could just decode it. The inside of a black hole might not be the cold, empty void we imagine. It could be a raging inferno waiting to incinerate anything that crosses the event horizon. This terrifying idea, known as the firewall paradox, erupted in 2012 when physicists Olmary, Marolf, Polchinski, and Sully, collectively called AMPS, realized that reconciling general relativity with quantum mechanics might demand a wall of searing high-energy particles just inside a black hole's boundary. Picture diving into what you thought was a calm ocean, only to hit a submerged sheet of flames the moment you break the surface. That's the firewall, a quantum cosmic booby trap that violates Einstein's equivalence principle, which says free-falling observers shouldn't detect anything unusual at the event horizon. The paradox arises from a tug-of-war between three seemingly unshakable principles. Quantum mechanics demand that information can't be destroyed, the no-cloning theorem forbidding perfect duplication of quantum states, and the smoothness of spacetime dictated by general relativity. AMPS argued that if Hawking radiation carries information out of the black hole, as holography suggests, then the particles just inside the horizon must be maximally entangled with those leaving. But those same interior particles must also be entangled with their doomed partners falling deeper into the hole. Quantum mechanics forbids this monogamy of entanglement. A particle can't be fully entangled with two different systems at once. The only escape, a violent severing of entanglement at the horizon, releasing enough energy to torch anything passing through. Yet firewalls aren't the only solution to this puzzle. Enter fuzzballs, string theory's radically different vision of black hole interiors, proposed by Samir Mather, fuzzballs replace the classic singularity with a dense, tangled knot of vibrating strings, a quantum hairball with no sharp boundary or smooth horizon. Instead of falling through an event horizon into nothingness, infalling matter would hit this fuzzy, stringy surface almost immediately, with all information smeared across its structure like graffiti on a cosmic wall. While firewalls preserve information by burning it into Hawking radiation, fuzzballs encode it directly in their topology, avoiding the entanglement paradox altogether. The implications for quantum gravity are profound. Firewalls suggest spacetime itself might shatter into a quantum inferno under extreme conditions, revealing a fundamental conflict between relativity and quantum theory. Fuzzballs, meanwhile, imply that black holes are entirely quantum objects with no classical interior, a vision where general relativity's smooth geometry gives way to stringy chaos long before you reach the horizon. Observational clues might one day settle the debate. If firewalls exist, merging black holes could emit brief bursts of high-energy radiation as their horizons interact, signatures future gravitational wave detectors might catch. Fuzzballs, on the other hand, might leave imprints in the gravitational echoes of collisions, their lack of clean horizons subtly distorting the spiraling death dance of binary black holes. For now, the firewall and fuzzball camps remain at an impasse, each offering a starkly different path toward unifying gravity and quantum mechanics. One paints black holes as cosmic traps with a lethal surprise at the gates. The other sees them as giant stringy tumors where spacetime itself dissolves. Both remind us that in the quest for quantum gravity, even the darkest objects in the universe refuse to go quietly into the night. What if space-time isn't woven from loops, strings, or triangles, but from something as simple as a child's connect-the-dots drawing? That's the startling vision of quantum gravity, a theory where the universe begins as a chaotic web of abstract points, utterly featureless, with no sense of distance or direction. Then, like water freezing into ice, these points suddenly snap into a rigid geometric structure, creating the familiar fabric of space and time as we know it. The key lies in the connections between these points or nodes. Early on, every node links randomly to every other, a buzzing, directionless graph where here and there have no meaning. But as the cosmos cools, these links begin to stabilize, locking into place like cosmic Velcro, and from this dynamical dance, geometry itself emerges. This idea isn't just poetic, it's grounded in the mathematics of spin networks, the same structures underpinning loop quantum gravity. Each node carries quantum spin degrees of freedom, and the links between them represent how space is stitched together at the tiniest scales. But quantum gravity takes this further, proposing that space isn't just a static network. It's a dynamical system undergoing a phase transition, like steam condensing into droplets. Before the transition, the universe is a soup of disconnected possibilities. After, it's a crystalline lattice where locality and dimensionality suddenly make sense. Condensed matter physics offers a striking analogy. Think of a magnet heating up until its atoms lose all alignment, their spins flipping chaotically. Cool it back down and the spins suddenly lock into order, creating a magnetic field. Quantum gravity suggests space itself behaves similarly, with links between nodes freezing into place not as spins but as the very threads of geometry. This could explain why we experience 3 spatial dimensions instead of, say, 10. Just as ice forms crystalline patterns instead of random shapes, the universe's graph might favor certain configurations purely through statistical inevitability. The theory even offers a fresh take on the Big Bang. Instead of a singular explosion, the birth of space-time could have been a gravity phase transition, a moment when the primordial chaos of disconnected nodes first crystallized into an ordered, low-entropy lattice. Intriguingly, remnants of this pre-geometric phase might linger in the universe's structure. Some models predict that defects in the graph, like cosmic cracks in the ice, could manifest as dark energy or even create exotic particles that only interact gravitationally. Yet challenges remain. How exactly does the smooth, curved space of general relativity emerge from this discrete graph? And can the theory reproduce the standard model's particles without ad hoc additions? Supporters point to hints in quantum error correcting codes where information is stored non-locally in networks, as a clue that quantum gravity might naturally encode matter as disturbances in space's fabric. Whether quantum gravity ultimately holds the key to quantum gravity or not, it embodies a thrilling idea that the universe's deepest order might not be written in the language of geometry, but in the silent, ceaseless rewiring of connections. A cosmic game of dot to dot where every line drawn creates reality itself. The quiet void between stars isn't really empty. It's constantly bombarded by cosmic rays, high-energy particles racing across the universe at nearly the speed of light. These intergalactic messengers might hold the key to unlocking quantum gravity's deepest secret, the energy scale at which space transitions from a chaotic web into the orderly geometry we know. If the theory's phase transition occurred at relatively low energy, say, within reach of the most powerful cosmic rays, these particles could betray subtle distortions as they traverse the universe's underlying graph-like structure. Imagine a cosmic ray proton traveling for millions of years, its path perfectly straight in classical space-time. But if space has a granular, graph-like foundation at certain energy thresholds, the proton's journey might occasionally stutter as it hops between nodes in the quantum network. These microscopic detours could accumulate over vast distances, leaving telltale fingerprints in the particle's arrival time or direction. Ultra-high-energy cosmic rays, those with energies exceeding 10 to the 18 electron volts, are ideal probes for this effect. At such extreme energies, the wavelength of the particle becomes small enough to potentially resolve the Planck scale, graininess of space, much like how fine sand reveals the texture of paper that's smooth to the naked eye. Experiments like the Pierre Auger Observatory in Argentina already monitor these cosmic rays for anomalies. While no definitive evidence of quantum gravity has emerged, some puzzling observations linger. A handful of ultra-high-energy events appear to arrive in clusters or from directions that don't align with known astrophysical sources. Could these be hints of space-time's hidden graph structure bending particles along unforeseen paths? Alternatively, if cosmic rays interact with remnant defects in the graph, like cracks in frozen ice, they might produce unexpected secondary particles or energy losses during atmospheric showers. There's a catch, though. Quantum gravity's energy scale might be far higher than even the most energetic cosmic rays can probe. If the phase transition occurred at the full Planck energy, 10 to the 19 times higher than what current detectors can measure, the theory would remain untestable with today's technology. But optimists point to condensed matter analogies. Phase transitions often happen at scales much lower than a system's maximum energy. Superconductivity, for instance, emerges at temperatures billions of times lower than the atomic energy scale. If space-time follows suit, cosmic rays might already be scraping the edge of quantum gravity's observable window. The search isn't limited to cosmic rays. Gamma ray bursts, the universe's most violent explosions, could also encode clues. If high-energy photons from these events traverse graph-like space, their polarization or spectral lines might carry subtle imprints of the network structure. Future observatories like the Cherenkov Telescope Array, with unprecedented sensitivity to gamma-ray nuances, could turn these speculations into data. Even if definitive proof remains elusive, the mere possibility reshapes how we view space-time. It suggests that the universe's smooth geometry might be a facade, a frozen accident in a much richer, more dynamic quantum landscape. And somewhere in the storm of particles raining down from the cosmos, the universe might be quietly confessing its true, tangled nature. What if everything you see around you, the stars, the trees, even your own hands, is nothing more than an elaborate illusion, a three-dimensional projection of information scribbled on a distant, two-dimensional surface? That's the jaw-dropping claim of the holographic principle, a theory so audacious it redefines reality itself. The idea first took root in the study of black holes, where physicists made a bizarre discovery. The entropy, the hidden information of a black hole, isn't proportional to its volume as you'd expect, but to the area of its event horizon. It's as if all the data about what fell into the black hole wasn't lost inside but got smeared onto its surface like cosmic spray paint on a spherical canvas. This revelation led to a radical question. If a black hole's interior can be perfectly described by information on its boundary, could the entire universe work the same way? Enter Juan Maldacena's AD/CFT correspondence, a mathematical tour de force that turned speculation into a concrete framework. Maldacena showed that a hypothetical universe with negative curvature, an anti-de Sitter space, could be entirely equivalent to a lower-dimensional quantum field theory living on its boundary. Picture a snow globe with an intricate winter scene inside. Now imagine that scene isn't really in the globe. It's encoded in flat, swirling patterns on the glass surface, and the 3D illusion emerges when you peer through it. That's AD/CFT in a nutshell. Gravity in the bulk universe is a shadow play cast by quantum particles dancing on a distant, flat stage. The implications are staggering. If true, the holographic principle means our 3D reality is a kind of cosmic mirage, a projection so flawless we'd never notice the seams. Black holes aren't just objects in this view, they're the universe's way of testing its own limits, revealing where the holographic code flexes and strains. Even time might be emergent, a secondary effect of deeper, timeless quantum interactions on the boundary. This isn't just philosophy, it's hard math with equations that link entangled quantum states on the boundary to geometric wormholes in the bulk, bridging quantum mechanics and general relativity in ways Einstein could never have imagined. Yet for all its elegance, the holographic principle leaves burning questions. Our universe isn't an anti-de Sitter space, it's expanding at an accelerating rate, better described by de Sitter geometry. Translating Maldacena's insights to our real cosmos remains a towering challenge, like trying to adapt a brilliant sonnet written in one language to another without losing its rhyme or rhythm. Some theorists speculate that our universe's boundary might lie not in space but in time, perhaps at the far future's infinite horizon, where all light and information ultimately collect. Others wonder if holography could explain dark energy, with the accelerating expansion arising from quantum information leaking between dimensions. Whether the holographic principle is the final word on quantum gravity or just a stepping stone, it's already reshaped how we see reality. It whispers that the universe's deepest truths might not live in the dimensions we experience, but in the hidden codes written at its edges. A cosmic reminder that sometimes the most profound discoveries come when we dare to question the very nature of space itself. The holographic principle isn't just a dazzling mathematical idea, it's a hypothesis that might actually leave fingerprints in the real world, traces we could detect with the right tools. Enter holometer experiments, audacious attempts to catch the universe's pixelation in action. Imagine trying to measure the fuzziness of a digital photo by zooming in until you see the individual pixels. Now imagine doing that for space-time itself. That's the goal of devices like Fermilab's holometer, a high-precision laser interferometer designed to hunt for holographic noise, the quantum jitter that would arise if space-time were fundamentally granular. At its core, the holometer splits a laser beam into two paths, then recombines them to detect minuscule fluctuations in the distance between mirrors. If space-time is truly pixelated at the Planck scale, these fluctuations wouldn't just be random, they'd carry a distinct statistical signature, a kind of quantum static whispering through the fabric of reality. It's akin to listening for the faint crackle of a vinyl record to prove music is stored in grooves, not magically conjured from air. Early results inconclusive. The noise detected so far could just as easily be instrumental artifacts or environmental vibrations, leaving the holographic interpretation tantalizingly out of reach. Critics dismiss these experiments as fringe science, arguing that Planck scale effects are too minuscule to manifest in tabletop setups. The Planck length is a staggering 10 to the negative 35 meters trillions of times smaller than what even the most sensitive interferometers can probe. Skeptics liken it to trying to hear a pin drop on the moon while standing in a hurricane. Worse, some accuse holographic noise models of being unnaturally fine-tuned, retrofitting predictions to explain null results rather than making bold, falsifiable claims. Yet supporters counter that emergent phenomena can amplify tiny effects. Just as a single water molecule doesn't make a wave, but trillions together create tsunamis, the collective behavior of Planck-scale grains might magnify into detectable signals. Analogies abound in condensed matter physics. No one observes individual atoms in a superconductor, but their collective behavior generates macroscopic zero resistance. Could space-time's granularity similarly scale up under certain conditions? Alternative approaches are pushing the envelope further. Quantum optics experiments exploit entangled photons to probe space-time structure, while atomic clocks placed in superposition states might reveal slight discrepancies in timekeeping caused by holographic fluctuations. Even gravitational wave detectors like LIGO, though designed for cosmic cataclysms, could inadvertently stumble upon anomalies hinting at space-time's underlying code. The debate crystallizes a deeper tension in physics. Should we chase theories that are elegant but untestable, or limit ourselves to ideas within experimental reach, even if they feel pedestrian? Holographic noise experiments, for all their controversy, dare to ask whether the universe's grandest ideas might leave footprints small enough to fit in a lab. Whether those footprints are real or mirages, the hunt itself reshapes how we imagine the boundaries, literally and figuratively, of reality. Deep in the equations of particle physics lies a hidden symmetry so perfect it could solve quantum gravity's fiercest paradoxes if only nature had bothered to use it. This is supersymmetry, or SUSY, a mathematical jewel that posits every known particle has a secret superpartner, a shadow twin differing only in spin. Electrons would pair with selectrons, quarks with squarks, and even gravity's hypothetical carrier, the graviton, would dance with the gravitino. At first glance, this seems extravagant, doubling the universe's particles for elegance alone. But SUSY magic lies in how it tames the monstrous infinities plaguing quantum gravity calculations. When particles and their superpartners interact, their contributions to quantum fluctuations cancel out with breathtaking precision, like two dancers whose missteps perfectly offset one another. Suddenly, equations that once exploded into nonsense converge into clean, finite answers. This balancing act isn't just mathematical sleight of hand. It's the reason supergravity, SUSY fusion with general relativity, became a leading candidate for quantum gravity in the 1980s. By weaving supersymmetry into gravity's fabric, theorists found a way to harmonize the unruly quantum world with Einstein's curved space-time. Supergravity's equations suggested extra dimensions could curl up in ways that naturally accommodated gravity's quantum behavior, offering a path toward unification without the complexity of string theory. For a time, it seemed the universe might truly be supersymmetric at its core. Then came the Large Hadron Collider. If SUSY existed, the LHC's proton collisions should have spawned superpartners at energy scales it could probe. Yet after years of smashing particles with enough force to recreate conditions a fraction of a second after the Big Bang, no squarks, photinos, or gravitinos materialized. The silence was deafening. Optimists note that SUSY might still lurk at higher energies, perhaps just beyond the LHC's reach, or that superpartners could be stealthier than predicted, evading detection through unexpected decays. Others propose split SUSY, where superpartners exist but with masses so vast they'd require colliders the size of the solar system to produce. The stakes couldn't be higher. Without supersymmetry, one of quantum gravity's most elegant solutions vanishes, leaving theorists to grapple with the messy infinities SUSY so neatly resolved. Yet even unproven, SUSY legacy endures. Its mathematics continue to inspire string theory and holography, while its failure to appear forces physics to confront uncomfortable questions. Is nature truly as symmetrical as we'd hoped? Or are we chasing mathematical beauty down a rabbit hole reality never dug? For now, supergravity remains a masterpiece of theoretical imagination, one waiting for the universe to either confirm its brilliance or reveal its next, even stranger act. Supersymmetry's vanishing act at the LHC doesn't necessarily mean it's dead, just that the theory might be playing hide and seek at energy scales we haven't probed yet. Picture a vast cosmic treasure map where the X marking SUSY superpartners isn't in the realm of tera-electronvolts where we've been digging, but far beyond, in the uncharted territory of petaelectronvolts or higher. Some theorists argue this isn't evasion but a natural consequence of SUSY elegance. The symmetry could be broken at energies so extreme that superpartners acquire masses far heavier than their standard model counterparts. In this scenario, the LHC's silence isn't a refutation but a clue, urging us to build even mightier colliders or rethink detection strategies. Supporters of high-energy SUSY point to the hierarchy problem, the puzzling gap between the weak nuclear force's energy scale and gravity's crushing Planck scale. Without SUSY cancellations, the Higgs boson's mass should skyrocket to Planckian levels due to quantum corrections, yet it sits curiously light. If superpartners exist at, say, 10 or 100 tera-electronvolts, they could still stabilize the Higgs without leaving traces in current data. The catch, testing such energies would require colliders with circumferences larger than small countries, a feat of engineering and funding that could take decades. Critics counter that a theory flexible enough to retreat indefinitely from experimental reach risks becoming untestable in principle, crossing into metaphysics rather than physics. Enter split SUSY, a clever compromise that salvages the theory's mathematical grace while dodging the LHC's null results. Proposed by theorists like Nima Arkani-Hamed and Savas Dimopoulos, this variant suggests that while most superpartners could be absurdly heavy, beyond direct detection, the lightest ones, like the neutralino or gluino, might linger at lower masses. These survivors could still explain dark matter or unify the fundamental forces without overburdening accelerators. The trade-off, SUSY's original promise of solving the hierarchy problem weakens, since the heaviest superpartners no longer shield the Higgs from quantum tumult. It's a bittersweet bargain: keep SUSY beauty but sacrifice some of its explanatory power. Meanwhile, alternatives to SUSY are gaining traction. Technicolor models, for instance, replace the Higgs mechanism with dynamic symmetry breaking, akin to how superconductivity emerges from electron interactions rather than a fundamental field. Extra-dimensional theories like Randall-Sundrum warped geometries offer their own hierarchy solutions, bending space-time itself to explain gravity's feebleness. Yet none of these alternatives have SUSY's sheer elegance or its seamless fusion with gravity in supergravity frameworks. The debate crystallizes a deeper tension in theoretical physics. Should we cling to beautiful ideas that resist scrutiny or pivot to messier models that fit the data? SUSY fate isn't just about particles, it's a referendum on how much weight we give mathematical harmony in deciphering nature's laws. As the next generation of experiments like the proposed future circular collider takes shape, the question lingers: is SUSY a delayed revelation or a cautionary tale about the allure of symmetry in an asymmetric universe? What if the quantum world isn't built on probabilities at all, but on something far more concrete: Causal fermion systems propose exactly that, weaving gravity and quantum fields into a single deterministic tapestry where everything from particles to space-time emerges from the dance of fermionic wave functions. Forget dice rolls and probability clouds. This framework treats quantum behavior as the inevitable outcome of deeper mathematical structures, like watching ripples form predictably when you toss a stone into a pond. At its heart, the theory replaces the abstract notion of quantum fields with concrete mathematical objects called fermionic wave functions. These aren't your textbook electrons buzzing around nuclei. They're more fundamental entities that encode both matter and the geometry of space-time itself. Picture each fermion as a tiny needle stitching together the fabric of reality, where every thread's position and orientation determine how space curves and particles interact. Unlike standard quantum field theory, where particles pop in and out of existence in a probabilistic haze, here everything evolves deterministically according to precise equations. No randomness, just cause and effect playing out on a cosmic scale. One of the theory's most striking features is how it banishes singularities, those problematic infinities haunting black holes and the Big Bang. In general relativity, when matter collapses under gravity, equations predict a point of infinite density where physics breaks down. But causal fermion systems prevent this catastrophic collapse through built-in mathematical constraints. The fermionic wave functions simply can't be squeezed beyond a certain limit, acting like cosmic bumpers that keep space-time smooth and finite. Black holes in this view wouldn't harbor singularities at their cores, but something akin to ultra-dense knots where fermions reach maximum packing density without ever tearing the fabric of reality. The framework also reimagines the nature of time. Instead of treating it as a background parameter or an emergent property, time arises organically from the causal ordering of fermion interactions. Imagine a vast domino rally where each tile's fall is dictated by the one before it. The sequence itself becomes the arrow of time, with no need for an external clock. This neatly sidesteps quantum gravity's infamous problem of time, where traditional approaches struggle to reconcile relativity's fluid time with quantum mechanics' static picture of evolution. Yet for all its conceptual elegance, causal fermion systems face skepticism. The deterministic approach clashes with quantum mechanics' probabilistic core, most famously enshrined in Bell's theorem, which suggests nature is fundamentally non-local and random. Proponents counter that the apparent randomness in quantum experiments could stem from our limited view of the fermionic landscape, much like how a strobe light makes continuous motion appear choppy. They also point to the theory's ability to reproduce key quantum phenomena, like superposition and entanglement, as mathematical inevitabilities rather than postulates. Practical challenges loom too. The equations governing fermionic interactions are notoriously difficult to solve, even for simple systems, leaving researchers to rely on approximations and numerical simulations. And while the framework unifies gravity with quantum fields conceptually, it hasn't yet produced testable predictions that distinguish it from rival theories, a hurdle that's kept it on the fringes of mainstream quantum gravity research. But the theory's audacity is its strength. By recasting space-time as a secondary effect of fermionic interactions, it flips the script on centuries of physics. Instead of asking how particles move through space, we're prompted to ask how space itself emerges from their relationships, a profound shift in perspective that could redefine what we consider fundamental. Whether causal fermion systems ultimately unlock quantum gravity's mysteries or inspire better models, they remind us that sometimes the universe's deepest truths hide not in the answers we've championed, but in the questions we've yet to ask the right way. Causal fermion systems dazzle with their mathematical elegance, every equation meticulously crafted to avoid the infinities and paradoxes that plague other quantum gravity approaches. The theory's deterministic core feels like a breath of fresh air in a field choked with probability clouds and unresolved singularities. By treating space-time as an emergent property of fermionic interactions, it sidesteps the conceptual quicksand of quantizing gravity altogether. There's a beauty to its austerity, a sense that the universe might truly be this orderly beneath the chaos we observe. Yet elegance alone doesn't guarantee truth. For all its internal consistency, the theory faces a formidable challenge. Can it make predictions distinct enough to test? Physics thrives on falsifiability. Our theory isn't just a pretty set of equations, but a lens through which we interrogate nature. So far, causal fermion systems have struggled to produce unambiguous signatures that would set them apart from competitors like string theory or loop quantum gravity. Take black holes, for instance. While the framework elegantly banishes singularities, its predictions for what replaces them, those ultra-dense fermion knots, don't yet translate into observable effects. Unlike Hawking radiation or gravitational wave echoes, which offer concrete experimental hooks, fermion-based black holes remain tantalizingly abstract. The trouble deepens when you consider quantum mechanics' most stubbornly verified feature, probabilistic behavior. From double-slit experiments to Bell test violations, nature seems insistently random at microscopic scales. Causal fermion systems argue this randomness is illusory, a consequence of hidden variables in the fermionic landscape. But replicating quantum correlations without violating known constraints like the no-signaling principle requires mathematical contortions that some critics find unconvincing. It's as if the theory demands we reinterpret decades of experimental results through a radically new lens, without yet providing a clear reason to do so. Then there's the computational barrier. Solving the theory's core equations for anything beyond simplified scenarios demands Herculean effort, leaving researchers to rely on approximations that might miss crucial features. Compare this to general relativity, where even rough calculations in the early 20th century yielded testable predictions like light bending around the sun that cemented Einstein's legacy. Without similar breakthroughs, causal fermion systems risk becoming a philosophical curiosity rather than a scientific revolution. Supporters counter that groundbreaking theories often outpace experiment. Dirac's equation predicted antimatter years before positrons were spotted in cloud chambers. Gravitational waves waited a century for detection. Perhaps fermion systems simply need time to mature. But with rival frameworks already offering testable ideas, from holographic noise to quantum bounce cosmologies, the clock is ticking. The theory's greatest strength, its mathematical purity, could also be its Achilles heel if it can't bridge the gap between abstraction and observation. Ultimately, the question isn't whether causal fermion systems are beautiful. It's whether beauty alone can carve a path through the messy, uncertain terrain of quantum gravity. The universe has a habit of favoring the pragmatic over the pristine, a lesson every theorist wrestles with in the quiet moments between equations. Shape dynamics dares to rewrite Einstein's playbook by proposing that gravity isn't about the curvature of space-time, it's about shapes and their transformations. At its core, this theory swaps general relativity's reliance on space-time's metric structure for a radical new priority, conformal symmetry, the idea that physics should stay unchanged even if you stretch or shrink distances uniformly, as long as angles remain preserved. Picture inflating or deflating a balloon covered in constellations. The stars' relative positions stay the same, their shapes unchanged even as the balloon's size shifts dramatically. Shape dynamics argues that this symmetry isn't just a curiosity but fundamental, with gravity emerging from the universe's insistence on preserving relational geometry rather than absolute scales. Where general relativity treats space and time as a unified, dynamical fabric, shape dynamics disentangles them, treating space as primary and time as a derived concept. This reversal isn't just philosophical, it's mathematically profound. the theory reconstructs Einstein's equations by demanding that physical laws remain invariant under local conformal transformations, effectively erasing any privileged notion of scale. In practice, this means two observers could disagree on the distances between objects, but as long as they agree on the angles between them, the shapes they form, their descriptions of gravity would be equally valid. It's a cosmic democracy of perspectives where rulers and clocks aren't absolute but negotiable. Remarkably, in classical regimes, shape dynamics reproduces the same predictions as general relativity. The orbits of planets, the bending of light around stars, even the spiraling dance of binary black holes, all match Einstein's framework to exquisite precision. But peel back the layers to the quantum realm, and the theories diverge starkly. General relativity's singularities, those infinitely dense knots where equations break down, simply don't arise in shape dynamics. Instead, the theory's conformal symmetry acts like a cosmic regulator, preventing collapse into infinite densities by enforcing a minimum shape resolution. Black holes, in this view, might not be bottomless pits but dense, finite structures where matter reaches a maximum packing density without ever violating physics rules. The real drama unfolds in quantum gravity. While general relativity struggles to reconcile its smooth geometry with quantum mechanics' granularity, shape dynamics offers a natural quantization path. By treating space as a network of conformal shapes, think of a cosmic connect-the-dots where only the angles matter. The theory sidesteps the problem of quantizing time altogether. Time emerges as a collective property of the system's evolving shapes, much like the flow of a movie emerges from individual frames. This could resolve long-standing paradoxes, like the problem of time in quantum cosmology, where traditional approaches clash over whether time is fundamental or illusory. Critics highlight the theory's untested nature. Without experimental signatures distinct from general relativity, shape dynamics risks being a mathematical repackaging rather than a revolutionary framework. Supporters counter that its true power lies in unification. By privileging shapes over metrics, it might seamlessly weave gravity into the quantum tapestry without extra dimensions or hidden particles. The debate isn't just academic, it's a battle over whether the universe's deepest secrets are written in the language of rulers and clocks, or in the timeless geometry of angles and scales. Whether shape dynamics ultimately triumphs or fades, it forces us to confront a provocative idea: that gravity's essence might not live in the stretch and warp of space-time, but in the unbreakable bonds of shape, an invisible hand ensuring that no matter how the universe expands or contracts, its deepest symmetries remain eternally, elegantly intact. Shape dynamics doesn't just reimagine gravity, it tackles one of quantum gravity's most perplexing puzzles head-on: the problem of time. In our everyday experience, time feels absolute, flowing forward like an unstoppable river. Yet in the equations of general relativity, time is just another dimension, malleable and relative. Quantum mechanics complicates things further with its static, timeless picture of reality, where the Schrödinger equation treats evolution as a parameter rather than a fundamental feature. The conflict reaches a boiling point in the Wheeler-DeWitt equation, a cornerstone of quantum gravity that famously lacks any reference to time at all. It's as if the universe's deepest laws have forgotten what clocks are for. This is where shape dynamics offers a startling way out. By prioritizing conformal symmetry, the preservation of angles over absolute scales, the theory effectively demotes time from a fundamental entity to an emergent property. Think of it like watching a flipbook animation. Each page is static, but flipping through them creates the illusion of motion. Similarly, shape dynamics suggests that what we perceive as time's flow is really the universe transitioning between distinct spatial configurations, each related by conformal transformations. The Wheeler-DeWitt equation's timelessness isn't a bug but a clue. time doesn't exist at the fundamental level. It arises from the way these shapes evolve relative to one another. The implications are profound. In quantum cosmology, where traditional approaches struggle to define, before the Big Bang, shape dynamics provides a natural framework. Without a fixed background time, the universe's birth isn't a singular event in a chronological sequence, but a particular configuration of shapes from which our arrow of time emerges. This sidesteps the need for exotic quantum tunneling from nothing scenarios, offering a cleaner, more geometric origin story. Even black holes, where general relativity predicts time's violent end at singularities, take on new life. Shape dynamics' conformal symmetry prevents infinite collapse, replacing the singularity with a dense but finite shape, a cosmic knot where time doesn't vanish but transforms. Critics argue that shape dynamics' time emergence feels too abstract, lacking the intuitive punch of familiar temporal flow. Yet supporters counter that our subjective experience of time might itself be an illusion, a cognitive byproduct of entropy increase in a universe built on deeper, timeless rules. After all, thermodynamics' arrow of time, why we remember the past but not the future, already suggests that time's flow is a statistical phenomenon, not a fundamental one. Shape dynamics simply extends this idea to gravity itself, weaving time's emergence into the very fabric of spatial relationships. The debate isn't just academic. If shape dynamics is correct, it could reshape how we simulate quantum gravity. Traditional lattice approaches struggle with time's role, often resorting to artificial, Euclidean time to make equations tractable. But shape dynamics' conformal methods might allow simulations where time arises naturally, like a melody emerging from notes rather than being imposed from outside. Future experiments, perhaps measuring subtle violations of Lorentz invariance or hunting for conformal signatures in cosmic microwave background data, could put these ideas to the test. Whether shape dynamics ultimately solves the problem of time or merely reframes it, the theory forces us to confront a radical possibility: that time's flow isn't woven into the universe's foundation, but is a secondary rhythm, a shadow cast by the ceaseless reconfiguration of space itself. It's a reminder that sometimes the most fundamental truths aren't in the forces we feel, but in the symmetries we've yet to see. What if gravity isn't carried by massless particles at all, but by something heavier? That's the bold premise of massive gravity, a theory where the hypothetical graviton, the quantum carrier of gravity, has a tiny but non-zero mass. At first glance, this seems like a minor tweak, but the implications ripple across the cosmos. Einstein's general relativity assumes gravitons are massless, which keeps gravity's influence infinite in range, perfectly matching Newton's inverse square law. But if gravitons weigh even a whisper, say 10 to the negative 33 electronvolts, gravity's behavior could shift dramatically over vast distances, potentially explaining dark energy's mysterious push without invoking exotic fields or cosmological constants. The math behind massive gravity is anything but simple. Unlike photons, which are easily described as massless particles in quantum electrodynamics, gravitons must mediate a force that bends space-time itself. Giving them mass introduces a slew of theoretical hurdles. For starters, a massive graviton would have 5 possible polarization states instead of the usual 2, complicating how it interacts with matter. Worse, early attempts at massive gravity equations often spawned ghosts, phantom fields with negative probabilities that threaten to unravel the theory's consistency. But breakthroughs in the 21st century, particularly the DRGT model named after de Rham, Gabadads and Tolley, tamed these ghosts by carefully constructing nonlinear interactions that cancel out the unphysical terms. The result, a theoretically viable framework where gravity's messenger isn't just a ripple in space-time but a particle with measurable heft. Observational consequences could be profound. If gravitons have mass, gravity waves wouldn't travel at light speed but slightly slower, with delays accumulating over cosmic distances. Binary pulsars, those precise cosmic clocks orbiting each other, serve as natural laboratories to test this. Their spiraling orbits, meticulously tracked for decades, emit gravity waves that should drain energy at rates exquisitely predicted by general relativity. Any significant deviation, like faster orbital decay, could hint at graviton mass. So far, pulsar data aligns with massless gravitons, but the window isn't fully closed. Minuscule masses, undetectable with current precision, might still lurk. Where massive gravity truly shines is in its potential to explain dark energy. If gravitons decay or interact weakly over vast scales, gravity's pull could weaken at cosmological distances, mimicking the repulsive effect we attribute to dark energy. Unlike the cosmological constant, which feels ad hoc to some theorists, this approach ties cosmic acceleration directly to gravity's quantum nature, the trade-off. Critics argue that fine-tuning is still required to match observations, and alternative explanations like modified Newtonian dynamics or quintessence fields remain competitive. Yet the theory's boldness is its allure. By challenging one of relativity's core tenets, massive gravity forces us to rethink not just how gravity works, but how deeply its quantum roots might shape the universe's grandest scales. Whether it survives future tests or collapses under observational pressure, it's a reminder that even the most familiar forces might still harbor secrets waiting to tip the scales of our understanding. Massive gravity's most infamous challenge isn't just giving the graviton mass, it's avoiding the spectral hitchhikers that haunted early attempts, ghosts. Not the kind that rattle chains or float through walls, but mathematical phantoms lurking in the equations, threatening to unravel the theory's very coherence. These ghosts aren't mere nuisances, they're fields with negative kinetic energy, particles that would drain energy from the universe like cosmic vampires, violating the sacred principle that probabilities must always add up to 1. Imagine a pendulum that swings higher with each pass, defying gravity without any input of energy, a physical impossibility. That's the chaos ghosts introduce, and in the early days of massive gravity, they seemed inevitable. The root of the problem lies in how gravity's quantum description splits into distinct polarization states. A massless graviton, like a photon, has two transverse polarizations, vibrations perpendicular to its direction of motion. But a massive graviton gains 3 extra states, 2 from longitudinal modes and 1 from a scalar component. This scalar is the troublemaker, behaving like a field with negative energy that grows uncontrollably over time, rendering the theory unstable. In the 1930s, physicists Wolfgang Pauli and Marcus Fiers identified this issue, and for decades it seemed insurmountable, like trying to build a bridge where one support beam actively sabotages the others. Enter the DRGT breakthrough. In 2010, Claudia de Ram, Gregory Gabadadze, and Andrew Tolley cracked the ghost problem by constructing a cunningly nonlinear version of massive gravity. Their key insight: the scalar ghost's destructive behavior could be tamed not by eliminating it, but by carefully tuning interactions between gravitons to cancel out the instability. Think of it like balancing a wobbly table. Instead of removing one leg, you adjust the others until the wobble vanishes. The DRGT model achieves this through a hierarchy of interactions, each layer mathematically sculpted to suppress the ghost's pathological tendencies while preserving healthy physical predictions. One elegant trick involves the graviton's self-interactions. In general relativity, gravity gravitates, it creates its own gravitational field. The DRGT framework extends this idea, engineering the graviton's mass term so that its nonlinearities act as a stabilizing counterweight. Picture a high wire walker using a pole to balance. The pole's weight introduces complexity, but that very complexity prevents a fall. Similarly, the graviton's mass term becomes a finely tuned instrument, balancing on the edge of instability without toppling over. But stability comes at a cost. The DRGT model's precision requires an almost artistic fine-tuning of parameters, raising eyebrows among physicists who prefer theories with natural, unforced elegance. Worse, some solutions exhibit bizarre behavior, like strong coupling. At low energies, a regime where quantum corrections overwhelm classical predictions, making calculations impossible without new physics. Critics argue this pushes the problem under the rug rather than solving it, while supporters counter that all breakthrough theories start with rough edges waiting to be polished. Observational tests remain scarce but tantalizing. If massive gravity is correct, gravitational waves from distant mergers might arrive slightly dispersed high-frequency ripples lagging behind low-frequency ones due to the graviton's mass. Current LIGO data shows no such delay, constraining the graviton's mass to vanishingly small values, but future detectors could probe even subtler effects. Cosmology offers another testing ground. Massive gravity modifies how structures form at vast scales, potentially leaving fingerprints in galaxy clustering or the cosmic microwave background's faint anisotropies. The ghost problem's resolution isn't just a technical triumph. It's a lesson in theoretical perseverance. Like sculptors chipping away at marble to reveal the form within, physicists carved through decades of dead ends to uncover a stable, if delicate, version of massive gravity. Whether this framework survives future scrutiny or inspires something even stranger, it proves a timeless truth. In physics, the most stubborn ghosts often lead to the most hauntingly beautiful breakthroughs. Einstein's general relativity paints gravity as the curvature of space-time, a bending and warping of the cosmic fabric that guides planets and light alike. But what if that's not the only way to tell the story? Teleparallel gravity flips the script, proposing that gravity isn't about curvature at all. It's about torsion, a twisting of space-time's geometry that gives gravity a whole new mathematical wardrobe. Imagine a cosmic game of telephone where instead of whispering through curved space, gravity's message gets passed along through a network of twisted connections, each link rotating slightly as the force propagates. At its core, teleparallel gravity, often abbreviated as TEGA, replaces Einstein's curvature-based framework with a geometric structure built on parallel transport. In general relativity, if you parallel transport a vector around a closed loop in curved space-time, it comes back slightly rotated, a hallmark of curvature. But in teleparallel gravity, space-time is flat, there's no curvature. Instead, gravity emerges from torsion, a measure of how much vectors twist as they move along paths in this geometry. It's like comparing a crumpled sheet of paper to a spiral staircase. Both can guide motion, but one relies on bends, the other on twists. The real magic happens in the math. Teleparallel gravity describes gravity using something called the Weissenberg connection, which zeroes out curvature entirely and encodes all gravitational effects in torsion. Strikingly, the equations spit out the same predictions as general relativity for everything from planetary orbits to black holes, meaning it's experimentally indistinguishable from Einstein's theory at classical scales. But peel back the quantum veil and the differences become tantalizing. Quantizing curvature, as in general relativity, leads to the notorious non-renormalizable infinities that have stumped physicists for decades. Torsion, on the other hand, plays far nicer with quantum field theory's renormalization tricks, offering a smoother path to a quantum theory of gravity. One of teleparallel gravity's biggest selling points is its simplicity in certain regimes. The theory's action, a measure of its dynamical content, boils down to a single scalar quantity called the torsion scalar, making it far more economical than general relativity's labyrinth of curvature terms. This streamlined structure isn't just mathematical eye candy, it's a pragmatic gift for theorists wrestling with quantum gravity. Where general relativity's complexity balloons when you try to quantize it, teleparallel gravity's leaner framework suggests a clearer route to unification, like swapping a tangled knot for a straight line. Yet the theory isn't without its skeptics. Some argue that teleparallel gravity's flat space-time feels like a sleight of hand, a clever redefinition that hides curvature's essence rather than replacing it. Others question whether torsion's quantum advantages will hold up under deeper scrutiny, noting that all approaches to quantum gravity hit snags eventually. But supporters counter that teleparallel gravity's resilience in reproducing general relativity's successes while dodging its quantum headaches makes it a contender worth taking seriously. Whether teleparallel gravity ultimately unseats curvature as gravity's true language or serves as a stepping stone to something even stranger, it's a reminder that sometimes the universe's deepest truths aren't about what you describe, but how you choose to describe them. And in the quest for quantum gravity, having multiple dialects might just be the key to deciphering reality's ultimate code. Teleparallel gravity doesn't stop at rewriting Einstein's rules. It opens the door to wild cosmic possibilities, like explaining dark energy without invoking mysterious substances or cosmological constants. This is where f of t gravity storms in, a bold extension that replaces teleparallel gravity's torsion scalar with a more general function, much like how f of r gravity tweaks general relativity. The result, a theory that might unify the universe's most baffling phenomena: inflation's explosive early expansion and dark energy's current acceleration under one geometric umbrella. Picture a cosmic engine where gravity's twists and turns don't just shape space-time but fuel its expansion, all encoded in the delicate dance of torsion. Critics, though, aren't so easily convinced. They argue that f of t gravity often feels like general relativity, wearing a clever disguise rephrasing curvature-based effects in the language of torsion without offering new physical insights. It's like translating a novel into another language word for word. The story doesn't change, just the syntax. When f of t models reproduce the same cosmic acceleration as a cosmological constant, skeptics shrug, asking why we'd abandon Einstein's simpler framework for a reinvention that doesn't yet solve quantum gravity's core problems. Yet supporters fire back with a compelling counter. Torsion's mathematical structure is inherently more quantum-friendly than curvature. While general relativity's infinities run rampant at high energies, f of t's linear equations might tame them, offering a smoother path to unification. Some versions even predict testable deviations like subtle shifts in gravitational wave propagation or anomalies in large-scale galaxy clustering. These aren't just abstract musings. Future telescopes like Euclid or gravitational wave detectors could spot the telltale cracks in Einstein's edifice, hints that torsion, not curvature, is gravity's true face. The debate crystallizes a deeper tension in physics. Is teleparallel gravity a revolutionary alternative or just a redundant reformulation? For now, the universe isn't telling. But whether f of t gravity ultimately reshapes our cosmic understanding or fades into obscurity, it proves a timeless truth. Sometimes, the most profound breakthroughs begin by questioning not just the answers we've found, but the language we've used to frame the questions. Simplicial quantum gravity takes the idea of a pixelated universe to a whole new level. Instead of loops, strings, or points, it imagines space-time as a patchwork of four-dimensional triangles glued together to form the fabric of reality. Picture a cosmic mosaic where each tile isn't a flat square but a hyper-dimensional simplex, a geometric building block that locks into its neighbors with mathematical precision. This lattice approach doesn't just approximate Einstein's smooth space-time. It reconstructs it from the ground up, like assembling a curved sculpture from countless tiny flat facets. What sets this framework apart is its numerical rigor. Unlike loop quantum gravity's abstract networks or string theory's unseen dimensions, simplicial quantum gravity thrives in the realm of supercomputers. Researchers can simulate these triangulated universes by defining rules for how simplices connect, then watching gravity emerge from their collective behavior. It's a bit like building a virtual cosmos in Minecraft, except the blocks obey quantum mechanics and the physics engine is general relativity. The equations governing these simulations are fiendishly complex, but when run at scale, they hint at something profound. The smooth space-time we experience might just be the statistical average of an underlying quantum frenzy, like the blur of a spinning top resolving into a single curve. Comparisons to causal dynamical triangulations are inevitable. Both theories chop space-time into geometric chunks, but the devil's in the details. Causal dynamical triangulations enforce strict cause and effect relationships between simplices, ensuring time only flows forward. Simplicial quantum gravity, meanwhile, often starts with Euclidean simplices, no built-in time direction, and lets chronology emerge dynamically. It's the difference between pre-writing a story's plot and tossing characters into a simulation to see what narratives arise. This flexibility makes simplicial approaches versatile but computationally brutal. Every new simplex added to the lattice exponentially increases the possible configurations, demanding ever more processing power. The numerical challenges here are staggering. To recover realistic physics, simulations must pass two critical tests. They need to exhibit dimensional reduction, where the jumble of simplices smooths into a four-dimensional universe at large scales, and reproduce Einstein's equations in the classical limit. Early results are promising, but fragile tiny tweaks to the lattice's rules can tip the cosmos into unphysical realms with too many dimensions or no coherent gravity at all. Some models sidestep these pitfalls by borrowing techniques from quantum field theory, treating the simplices as fields vibrating in an abstract space. Others introduce matter as defects in the lattice, like knots in a net that warp the surrounding geometry. Yet for all its computational might, simplicial quantum gravity faces a philosophical hurdle. Is space-time truly a lattice, or is the lattice just a calculational tool? Skeptics argue that the theory's reliance on fixed geometric forms feels artificial, a convenient approximation rather than a fundamental truth. Supporters counter that all physics is approximation, and what matters is whether the math mirrors nature. The debate echoes centuries of tension between discrete and continuous views of reality, from atomism to fluid dynamics. Where the theory shines is in its concrete testability. Unlike some quantum gravity candidates that dwell in unreachable energy scales, simplicial models leave fingerprints we might one day detect: anomalies in cosmic ray propagation, subtle deviations in gravitational wave signals, or even relics of a lattice-like structure in the cosmic microwave background. The road ahead is steep, but the payoff could be revolutionary. A universe where gravity isn't just a force or a curvature, but the collective rhythm of countless quantum triangles clicking together in the dark. The key to unlocking quantum gravity might lie not in complex equations, but in the hidden patterns that emerge when countless tiny pieces click together. Just as swirling water molecules suddenly coalesce into a smooth, flowing river. This is the tantalizing promise of phase transitions in simplicial quantum gravity. The idea that if we simulate the universe's building blocks with enough precision, the chaotic jumble of geometric fragments will spontaneously organize into the four-dimensional space-time we recognize. It's like watching ice crystals form in reverse, starting with a frenzied atomic dance and ending with something perfectly continuous and predictable. Computational models of these lattice universes reveal something extraordinary. When the quantum connections between simplices reach a critical density, the system undergoes a phase transition, a dramatic shift where disorder gives way to order, and the jagged edges of the lattice dissolve into an emergent smoothness. Imagine zooming out from a pointillist painting. Up close, it's just a mess of colored dots, but step back and a coherent image materializes. That's the continuum limit physicists are chasing, a mathematical tipping point where the universe's pixelated foundation becomes indistinguishable from the seamless cosmos Einstein described. Yet reaching this limit is no simple task. The simulations must walk a razor's edge. Too few simplices and space-time remains fractured. Too many, and the equations collapse under their own complexity. It's like tuning a radio to the exact frequency where static resolves into music, except the dial controls the fundamental nature of reality. Some models suggest this critical point might be governed by an underlying conformal symmetry, a kind of cosmic rule that ensures angles and proportions stay consistent even as the lattice fluctuates. If true, it would mean the smoothness of space-time isn't an accident but a mathematical inevitability, written into the fabric of quantum geometry itself. The implications ripple across physics. If continuum limits can be rigorously demonstrated, they'd bridge the gap between quantum mechanics and general relativity, not by force, but by emergence, proving that Einstein's equations aren't fundamental laws, but the macroscopic echo of deeper, granular rules. Black holes, singularities, even the Big Bang might look radically different in this light, not as infinite breakdowns, but as natural consequences of space-time's underlying structure straining under extreme conditions. But challenges loom. Current simulations struggle to achieve the necessary scale, with computational power lagging behind the theory's ambitions. And skeptics question whether continuum behavior in these models is genuine or just an artifact of approximation, like mistaking a polygon with a million sides for a true circle. The real test will come when predictions deviate from classical relativity in ways experiments can detect, perhaps in subtle gravitational wave anomalies or unexpected correlations in cosmic microwave background data. For now, phase transitions in simplicial quantum gravity remain a breathtaking gamble, a bet that the universe's deepest secrets aren't hidden in the equations we've yet to write, but in the patterns we've yet to simulate. And if the numbers align, we might finally witness the moment when chaos becomes cosmos, and quantum fragments stitch themselves into the smooth, starry expanse we call home. What if gravity wasn't just one color, but an entire spectrum? That's the striking vision of rainbow gravity, a theory proposing that space-time isn't a uniform fabric but a textured canvas where gravity's strength depends on the energy of the particles moving through it. Imagine a prism bending light into a rainbow, except instead of light, it's the gravitational field itself that splits into different colors, with high-energy particles experiencing space-time differently than low-energy ones. A gamma-ray photon racing from a distant explosion wouldn't just traverse space, it would navigate a cosmic gradient where gravity's grip tightens or loosens based on its own energy. This radical idea springs from the marriage of general relativity and something called doubly special relativity. While Einstein's relativity introduced the speed of light as a universal constant, doubly special relativity adds a second invariant, the Planck energy, a staggering threshold where quantum gravity effects dominate. In this framework, particles with energies approaching this limit don't just move through space-time, they reshape it around them, like a speedboat churning water into turbulent wakes. Rainbow gravity takes this further, suggesting these distortions aren't mere noise but the key to gravity's quantum nature. The theory's name isn't just poetic, it hints at observable consequences. If gravity truly varies with energy, then two photons emitted simultaneously from a gamma-ray burst but with different energies should arrive at Earth at slightly different times. The high-energy photon, feeling a stronger gravitational pull from the universe's structure, might lag behind its lower-energy counterpart. This energy-dependent delay, called dispersion, would be the smoking gun, a cosmic rainbow signature etched into the light of cataclysmic events. Current telescopes like the Fermi Gamma-Ray Space Telescope have hunted for these delays, but results remain inconclusive. Some bursts show tantalizing hints of dispersion, while others stubbornly align with Einstein's classic predictions. Critics argue these anomalies could stem from astrophysical processes within the bursts themselves, like internal shock waves or magnetic field interactions rather than exotic gravity. Supporters counter that future observatories with sharper time resolution and broader energy coverage might finally catch gravity's spectrum in the act. Rainbow gravity's boldest claim isn't just about photons, it reimagines black holes. Near the singularity where particle energies skyrocket, the theory suggests gravity's color shift could prevent infinite collapse. Instead of a crushing singularity, you'd get a rainbow star, a dense remnant where gravity's varying strength balances matter's inward plunge. It's as if the universe has a built-in safety valve, tuning gravity's intensity to avoid its own destruction. Yet the theory walks a tightrope. By modifying general relativity to accommodate energy-dependent effects, it risks undermining the very principles that make Einstein's equations so robust. Why should gravity care about a particle's energy when it's mass that traditionally dictates its pull? Defenders argue this isn't a bug but a feature, a glimpse of quantum gravity's deeper rules, where energy and geometry intertwine in ways classical physics can't fathom. Whether rainbow gravity ultimately paints the universe's true portrait or fades into the palette of discarded ideas, it challenges a fundamental assumption that gravity is a monochrome force indifferent to the particles it bends. In a cosmos teeming with color, why shouldn't its most mysterious force shimmer with hidden hues? The answer might be written in the next gamma-ray burst's afterglow waiting for us to decipher its vibrant code. Rainbow gravity's energy-dependent space-time doesn't just tweak Einstein's rules, it threatens to shatter one of relativity's most sacred pillars, Lorentz symmetry. This cornerstone principle states that the laws of physics remain identical for all observers moving at constant speeds, no matter their velocity or direction. It's why time slows down for an astronaut racing near light speed, or why particles in a collider obey the same rules whether they're moving toward you or away. But if gravity's strength varies with a particle's energy, as rainbow gravity proposes, then two observers measuring the same event could get radically different results, breaking the cosmic democracy that's underpinned physics for over a century. Proponents argue this isn't a violation but an evolution of relativity. Just as Einstein generalized Newton's laws to include high velocities, rainbow gravity might extend relativity to incorporate Planck scale effects. The key lies in doubly special relativity, which posits that alongside the speed of light, the Planck energy acts as a second universal constant. At everyday energies, Lorentz symmetry holds perfectly, space-time behaves as Einstein predicted. But near the Planck scale, particles effectively feel a different geometry, like a surfer riding a wave that changes shape based on their speed. In this view, Lorentz symmetry isn't broken. It's energy-dependent, a subtle distinction that preserves its mathematical essence while accommodating quantum gravity's granularity. Critics aren't convinced. They point to gamma-ray bursts, cosmic explosions whose photons arrive at Earth after traveling billions of light-years. If high-energy photons experienced stronger gravitational slowing, as rainbow gravity suggests, they'd lag behind lower-energy ones. Yet observations from Fermi LAT and other telescopes show no consistent dispersion patterns. Some bursts display delays, but these could stem from astrophysical noise, magnetic field interactions, or shock waves within the bursts themselves rather than fundamental physics. Worse, modified dispersion models often require fine-tuning to match null results, eroding the theory's predictive power. The debate crystallizes a deeper tension in theoretical physics. Should we cling to symmetries that have survived every test for a century, or dare to modify them in pursuit of deeper truths? History offers cautionary tales. When Paul Dirac combined quantum mechanics with special relativity, his equations predicted antimatter, a seemingly outlandish idea later confirmed in experiments. But for every Dirac, there are dozens of theorists whose beautiful symmetries collapsed under empirical scrutiny. rainbow gravity's fate hinges on whether nature cares more about mathematical elegance or the messy, unscripted behavior of particles at the universe's extremes. One compromise emerges from string theory's playbook. Lorentz symmetry could be an emergent property, exact at low energies but approximate near the Planck scale. Imagine a frozen lake, perfectly smooth when you skate across it, yet under a microscope, riddled with cracks and imperfections. Similarly, space-time's Lorentz invariance might be a low-energy illusion, masking a fractured, energy-sensitive reality beneath. This approach dodges the gamma-ray constraints by pushing rainbow effects beyond observable energies while preserving the symmetry's usefulness in our classical universe. Yet, even if rainbow gravity falters, its legacy endures. By questioning Lorentz symmetry's inviolability, it forces us to confront whether our most cherished principles are absolute or merely provisional, a stepping stone to something stranger. The universe, after all, has never been shy about appending our assumptions. Whether through rainbow gravity or some yet unknown framework, the quest to reconcile relativity with quantum gravity guarantees one thing: the cosmos still has surprises up its sleeve. Imagine throwing a ball, and instead of arcing smoothly through the air, it vanishes from your hand and instantly reappears in your friend's grasp, no motion in between. That's the kind of cosmic sleight of hand non-local gravity proposes, where gravity's influence isn't bound by the speed of light or the familiar rules of cause and effect. Unlike Einstein's general relativity, where gravitational waves ripple outward at light speed, non-local gravity suggests the force can leap across vast distances in an instant, as if space-time itself has hidden shortcuts stitching the universe together. This isn't just a wild thought experiment, it's a serious attempt to solve some of gravity's thorniest puzzles, like the singularity inside black holes or the Big Bang's explosive origin, by erasing the very notion of here and there at the deepest levels. The theory's roots dig into quantum mechanics' strangest feature, entanglement. When two particles become entangled, measuring one instantly affects its partner, no matter how far apart they are. Einstein famously called this spooky action at a distance, but experiments have confirmed it's real. Non-local gravity takes this quantum weirdness and scales it up to cosmic proportions, proposing that gravity, too, might operate through invisible connections that bypass space-time's usual rules. Picture the universe as a vast network of quantum threads, where planets and stars don't just pull on each other through curved space, but are intimately linked by a web of instantaneous interactions. Black holes, in this view, wouldn't crush matter into singularities. Their gravitational reach would be non-local, spreading their influence far beyond their event horizons in ways that defy classical physics. Critics, however, pounce on the elephant in the room: causality. If gravity acts instantaneously, what stops the universe from descending into chaos, with effects preceding causes and paradoxes unraveling reality itself? Defenders argue that non-local gravity might appear a causal from our limited perspective, just as quantum entanglement seems to violate locality until you realize the system as a whole respects deeper, hidden symmetries. Some models even suggest non-locality could be a built-in feature of quantum gravity, with singularities acting as mathematical warnings that we've hit the limits of a local description, not the limits of physics itself. It's like realizing a movie's plot holes vanish when you notice the film is actually a hologram projected from a higher dimensional code, yet the theory's boldness comes with hurdles. Without a clear mechanism to explain how non-local gravity avoids contradictions like a star's gravity affecting another before it even forms, the framework risks feeling more like metaphysical poetry than testable science. Some attempts to ground it lean on holographic principles, where non-locality emerges from information being processed on a distant boundary, or on modified versions of Einstein's equations that introduce memory terms linking past and future gravitational states. But until experiments detect signatures, perhaps anomalies in gravitational wave signals or unexpected correlations in cosmic structure, non-local gravity remains a tantalizing what-if at the frontier of physics. What makes the idea so compelling despite the challenges is its audacious rethinking of connectivity. Maybe gravity isn't a force traveling through space at all, but a silent conversation happening beneath it where the universe's distant parts whisper to each other faster than light should allow. Whether this vision holds up or crumples under scrutiny, it's a reminder that sometimes the most radical answers lie not in refining old rules, but in daring to imagine the threads tying reality together might be far stranger and far more instantaneous than we ever dreamed. Non-local gravity doesn't just rewrite the rules for black holes or quantum entanglement. It could upend our understanding of the cosmos itself, offering radical alternatives to cosmology's biggest mysteries, dark matter and dark energy. Picture a galaxy spinning so fast its stars should fling into the void, yet something invisible holds them in place. Conventional physics invokes dark matter, an elusive substance outweighing ordinary matter 5 to 1. But what if the extra gravity isn't from hidden particles at all, but from the universe's hidden connectedness? Non-local gravity suggests that galaxies might be stabilized by gravitational echoes, tugged not just by nearby matter, but by distant masses via instantaneous links woven into space-time's fabric. It's as if every star feels the pull of every other star, no matter how far, through a cosmic web of unseen threads. This idea isn't just poetic, it's mathematically tangible. Some models replace dark matter's gravitational influence with non-local terms in Einstein's equations, effectively letting galaxies borrow gravity from distant cosmic structures. For example, a star orbiting a galaxy's edge wouldn't just respond to the visible mass inside its orbit, but to the universe's entire mass distribution, folded into the equations through retarded and advanced potentials. These terms act like gravitational memory, where past interactions leave imprints that linger and shape future motion. The result, rotation curves flatten exactly as observed without invoking invisible matter. Critics argue this smacks of fitting the data, but supporters counter that non-locality is no more ad hoc than inventing a particle we've never detected. Dark energy's accelerating expansion might also yield to non-local explanations. Instead of a cosmological constant or mysterious quintessence fields, the universe's push could stem from gravity's non-local tail, delayed interactions where distant regions of space-time influence each other across billions of years. Imagine tossing a pebble into a pond, but the ripples circle back to push the pebble outward. Similarly, non-local gravity could generate self-reinforcing feedback loops where the universe's expansion fuels further expansion, mimicking dark energy's effects. Some formulations even tie this to the holographic principle, where boundary effects on a cosmic scale manifest as accelerated expansion in the bulk. Yet the math is far from tidy. Non-local terms introduce integral differential equations, nightmarish combinations of derivatives and integrals that resist exact solutions. Unlike Einstein's elegant field equations, which relate local curvature to local matter, non-local gravity demands knowledge of the universe's entire history to compute present-day effects. Solving these equations often requires brutal approximations or restrictive symmetries, like assuming a homogeneous universe, which gloss over the messy reality of cosmic structure. Worse, poorly handled non-locality can spawn runaway solutions or violate energy conservation, creating mathematical ghosts as troubling as the singularities the theory aims to avoid. The debate mirrors centuries of tension between simplicity and completeness. Newton's gravity was clean but incomplete. Einstein's relativity fixed it but added complexity. Non-local gravity might be the next step, a framework so rich it captures phenomena we've had to invent dark matter and dark energy to explain, yet so intricate it teeters on the edge of calculational chaos. Whether it ultimately triumphs or collapses under its own weight, it forces us to confront a provocative idea that the universe's greatest mysteries might not stem from what's missing, but from connections we've yet to see. What if gravity isn't governed by a single set of rules, but by two? That's the mind-bending premise of bimetric gravity, a theory where space-time isn't described by one metric, the mathematical tool Einstein used to define curvature, but by two separate yet intertwined geometries. Imagine the universe as a theater with two overlapping stages, one where matter dances to the familiar rhythms of general relativity, and another where gravity itself moves to a different, quantum-friendly tune. These two metrics don't exist in isolation. They interact, influence each other, and together might hold the key to bridging the chasm between Einstein's cosmos and the quantum realm. The magic happens in how these metrics couple. One metric, call it G, describes the geometry matter perceives, the curved space-time that guides planets and bends light. The other, F, governs gravity's quantum behavior, operating at scales so tiny they'd make an atom look planetary. Normally, these metrics would clash, like two conductors leading an orchestra in different time signatures. But bimetric gravity introduces an elegant solution, a carefully tuned interaction term that lets the metrics harmonize at large scales, reproducing general relativity, while allowing quantum fluctuations to dominate at microscopic ones. It's as if space-time has a built-in translator, smoothing conversations between the classical and quantum worlds. One compelling version of this idea comes from physicists Claudia de Ram, Gregory Gabadadze, and Andrew Tolley d'Argenti massive gravity, who showed how bimetric theories can avoid the ghosts and instabilities that plagued earlier attempts. Their math reveals a surprising twist. The F metric doesn't just tweak gravity, it generates an effective gravitational medium that filters out pathological quantum fluctuations. Think of it like a cosmic noise cancellation system, where destructive interference removes the infinities that normally wreck quantum gravity calculations. The result, black holes without singularities and a Big Bang that might not have been a true singularity at all. Critics argue the theory feels like a mathematical sleight of hand, an ad hoc stitching of two frameworks rather than a unified whole. But supporters counter that bimetric gravity's dual structure mirrors nature's other dualities, like wave-particle duality or the holographic principle. After all, if light can be both particle and wave, why shouldn't space-time have two faces? The theory's real test lies in unique predictions, subtle differences in gravitational wave propagation, or anomalies in how galaxies cluster at cosmic scales. Future gravitational wave detectors like LISA or precision surveys of the cosmic web might one day spot these fingerprints, evidence that we've been living in a double-layered universe all along. What makes bimetric gravity so tantalizing is its refusal to accept the either-or dichotomy of modern physics. Instead of forcing quantum mechanics into relativity's curved mold or vice versa, it suggests a cosmos where both coexist through an intricate geometric duet. Whether this dance ultimately reveals nature's deepest secrets or falters under closer scrutiny, it reminds us that sometimes the most profound truths emerge not from simplifying, but from embracing complexity in harmony. The Weinstein mechanism acts like a cosmic mute button, suppressing strange new gravitational behavior in familiar places like our solar system, only to unmute it when we zoom out to the vastness of galaxies and beyond. Here's how it works. Imagine gravity as a ripple in a pond. Near the source, say, a planet or star, these ripples should follow Einstein's well-tested rules. But modified gravity theories often introduce extra waves that, if left unchecked, would wildly alter orbits or the bending of starlight. That's where the Weinstein effect steps in. It creates an invisible bubble around massive objects, a zone where these exotic gravitational fluctuations get dampened so severely they become undetectable. Within this bubble, general relativity reigns unchallenged, preserving the precise planetary motions and light deflection we've measured for centuries. This isn't just theoretical sleight of hand, it's a mathematical inevitability in certain modified gravity frameworks, like massive gravity or certain brain-world models. The mechanism relies on nonlinear interactions, where the very strength of gravity near massive objects reshapes how the additional gravitational modes propagate. Picture a crowd cheering at a stadium. Up close, individual voices blur into a roar, drowning out any single shout. Similarly, the Weinstein zone's high gravitational density smothers deviations from Einstein's predictions, ensuring Mercury's orbit and GPS satellite timing stay flawlessly on script. But venture beyond this zone into the near-empty voids between galaxies or the cosmic web's sprawling filaments, and the hidden aspects of gravity finally break free. Here, where matter is diffuse and gravity weak, the Weinstein suppression lifts. Modified gravity's exotic terms dominate, potentially explaining cosmic acceleration without dark energy or tweaking galaxy rotation curves sans dark matter. It's like removing noise-canceling headphones. Suddenly, you hear the universe's background hum, revealing gravitational behaviors that were always there but silenced locally. Critics argue this selective muting feels suspiciously convenient, a way to dodge tight solar system tests while flexing freedom on galactic scales. Yet supporters counter that the mechanism isn't arbitrary. It emerges naturally from the equations, much like how quantum effects fade to classical physics at larger scales. The real test lies in astrophysical edge cases, regions where the Weinstein radius brushes against observable phenomena. Dwarf galaxies, for instance, hover near this threshold, compact enough to feel suppression but diffuse enough that modifications might peek through. Subtle anomalies in their dynamics or gravitational lensing could betray the mechanism's handiwork. The Weinstein mechanism's brilliance lies in its duality, a cosmic Jekyll and Hyde that lets gravity wear two faces. One for the orderly neighborhood of stars and planets, another for the universe's wild, uncharted frontiers. Whether it's nature's elegant solution or a clever workaround awaiting falsification, it forces us to confront a humbling truth, that gravity's full story might still be hiding in plain sight, masked by the very laws we thought we'd mastered. Einstein's general relativity gave us a universe where gravity is the curvature of space-time, a smooth, twisting fabric shaped by mass and energy. But what if that fabric isn't just bending? What if it's also twisting, like a cosmic rope fraying under the spin of every electron, quark, and neutrino? That's the radical shift proposed by quantum Einstein-Cartan theory, a framework where gravity isn't just about where matter is, but how it's spinning. Here, space-time doesn't just curve, it develops torsion, a geometric kink generated by the intrinsic angular momentum of fermions, the particles that make up everything from stars to your own DNA. This isn't just a minor tweak to Einstein's equations. It's a full-scale reimagining of how matter and geometry interact. In general relativity, torsion is strictly zero. Space-time bends, but it doesn't twist. Quantum Einstein-Cartan theory, though, embraces torsion as a fundamental feature, with every spinning particle leaving a microscopic imprint on space-time structure. Picture a glass of water with countless tiny whirlpools, each stirred by the spin of passing particles. These subatomic vortices might be imperceptibly small, but collectively they could reshape the universe's largest-scale behavior. The implications are profound, especially in the extreme environments of the early universe. Near the Big Bang, when matter was compressed to unimaginable densities, fermions would have been packed so tightly their spins could have woven space-time into a knotted, torsion-rich landscape. This could have prevented the formation of singularities, those infinitely dense points where general relativity breaks down. Instead of collapsing into a mathematical nightmare, the universe might have rebounded in a quantum bounce, with torsion acting like a cosmic spring, resisting infinite compression. It's a dramatic alternative to the standard inflationary narrative, offering a way to avoid the Big Bang's existential nothingness by replacing it with a prior phase of cosmic contraction. But how does this differ from other torsion-based theories like teleparallel gravity? The key lies in the quantum connection. While teleparallel gravity uses torsion to replace curvature entirely, quantum Einstein-Cartan keeps both torsion and curvature coexist, each playing distinct roles. Torsion dominates at microscopic scales where particle spins matter most, while curvature takes over in the classical realm of planets and black holes. This duality makes the theory uniquely suited to bridge quantum mechanics and general relativity, offering a path to quantum gravity that doesn't require extra dimensions or unseen particles, just a deeper understanding of the space-time we already inhabit. Critics, though, point to the elephant in the room. If torsion is everywhere, why haven't we detected it? The challenge is scale. Torsion's effects are vanishingly small in today's sparse universe, like trying to hear a whisper in a hurricane. Yet there are hints. Some models suggest that torsion could subtly alter neutron star interiors, where fermions are densely packed, or leave faint imprints on gravitational waves from colliding black holes. Others speculate that cosmic microwave background anomalies, those faint asymmetries in the afterglow of the Big Bang, might bear torsion's fingerprints. The real allure of quantum Einstein-Cartan theory isn't just in its predictions, it's in its philosophical shift. By tying gravity directly to the quantum spins of matter, it suggests that space-time isn't a passive stage but an active participant in the universe's quantum dance. Whether this vision survives future tests or not, it reminds us that sometimes the most revolutionary ideas aren't about adding new layers to reality, but about seeing the old ones in a radically new light. Spin networks aren't just abstract mathematical constructs, they're the scaffolding of reality itself in loop quantum gravity. Picture space-time not as a smooth canvas but as a vast, intricate tapestry woven from threads of quantum angular momentum. Each thread represents a spin, a fundamental unit of rotation that links together to form a dynamic, ever-changing network. These aren't spins in the classical sense, like a top twirling on a table, but quantized properties that define how space itself is stitched together at the tiniest scales. When particles interact or gravity bends light, it's not happening on a featureless backdrop. It's the spin network vibrating, reconfigured by the universe's quantum dance. Now, throw torsion into the mix, the twisting of space-time introduced by quantum Einstein-Cartan theory, and these spin networks take on a whole new dimension. Imagine the threads of the tapestry aren't just connected but also coiled, like microscopic springs storing energy in their twists. This torsion could resolve one of general relativity's most infamous breakdowns, the singularity. Inside black holes or at the Big Bang, where Einstein's equations predict infinite density, spin networks with torsion might refuse to collapse into oblivion. Instead, the twisting geometry could act like a cosmic safety net, reaching a maximum curvature and then rebounding. It's as if space-time itself has a built-in resilience, a quantum memory that says, this far, no farther. The real magic happens when you ask how these twisted spin networks behave under extreme conditions. Near a black hole's core, for example, torsion could turn the singularity into a high-density knot of spin threads, where gravity's crush is counterbalanced by the torque of space-time itself. This isn't just theoretical hand-waving equations. In quantum Einstein-Cartan theory show torsion generating repulsive effects at ultra-small scales, like a coiled spring pushing back when compressed too tightly. Loop quantum gravity traditionally handles singularities by quantizing area and volume, but adding torsion introduces a second layer of protection, a geometric resistance to infinite collapse that's baked into the fabric of space-time. Critics, though, point to a glaring question. If torsion is so crucial, why haven't we seen its fingerprints? The challenge is one of scale. torsion's effects are drowned out in today's cold, sparse universe where matter is too diffused to twist space-time noticeably. But rewind to the Big Bang's seething quantum foam or peer into the heart of a neutron star, and the story might change. Some models predict that torsion could subtly alter gravitational waves from colliding compact objects or leave faint echoes in the cosmic microwave background like whispers from a time when space itself was a writhing, spinning sea. What makes this synthesis of spin networks and torsion so compelling isn't just its mathematical elegance, it's the way it reframes our cosmic origin story. The Big Bang might not have been a singular explosion from nothing, but a quantum bounce, a moment when the universe's spin networks, taut with torsion, reached their limit and sprang back outward. Black holes wouldn't be dead ends, but cosmic transformers, their singularities replaced by turbulent vortices of spinning geometry. The universe, in this view, isn't just expanding, it's vibrating, twisting, and remembering, a dynamic web of quantum threads where every loop tells a story. Horovà's foliation-based gravity isn't just another tweak to Einstein's equations, it's a full-throttle rewrite of space-time's rulebook. Imagine slicing the universe like a loaf of bread, where each slice represents a moment in time rigidly separated from the others. This isn't just a visual metaphor, it's the core of Horovà Lifshitz gravity, a theory that dares to break one of physics' most sacred symmetries, Lorentz invariance, in exchange for a prize theorists have chased for decades, renormalizability. In plain terms, it's a gamble that gravity's quantum chaos can be tamed by treating time as fundamentally different from space, a heresy in Einstein's relativistic world where the two blend seamlessly. At the heart of this idea is foliation, a geometric trick where space-time splits into stacked three-dimensional hypersurfaces, each representing now at different instants. Unlike general relativity's flexible, dynamic space-time, these slices are absolute. Time becomes a master clock ticking uniformly across the cosmos. The trade-off is stark. By sacrificing Lorentz symmetry, the principle that the laws of physics stay the same for all observers moving at constant speeds, Horovà's framework gains a powerful advantage. Gravity's equations, normally riddled with infinities at quantum scales, suddenly become well-behaved and computable. It's as if the theory swaps the universe's fluid, relativistic dance for a rigid, quantum-friendly grid, where time's fixed rhythm keeps gravity's wildest fluctuations in check. The magic lies in the way the theory treats high-energy regimes. Near the Planck scale, where quantum gravity effects dominate, Horovà's equations introduce higher-order spatial derivatives, terms that act like cosmic shock absorbers, damping out the infinite probabilities that plague traditional approaches. These terms break Lorentz invariance explicitly, but they also suppress the ultraviolet divergences that have stymied quantum gravity for nearly a century. Picture a chaotic crowd suddenly forced to move in lockstep. The disorder vanishes, replaced by orderly motion. But this rigidity comes at a cost. Without Lorentz symmetry, particles moving at different speeds could experience fundamentally different physics, a potential disaster for a theory meant to describe the universe universally. Critics argue that even tiny Lorentz violations should have been spotted in particle collisions or cosmic rays by now. Yet experiments like the LHC and Fermi Gamma-Ray Space Telescope show no such signs. Defenders counter that the symmetry might only break meaningfully at energies so high they're beyond current detection, leaving everyday physics untouched. It's a delicate balancing act. The theory must distort space-time symmetry just enough to tame quantum gravity, but not so much that it contradicts a century of precision tests. Where Horovà's ideas truly shine is in cosmology. The early universe, a hot soup of extreme energies, might have been governed by this foliated gravity, with its rigid time slices naturally driving inflation. The exponential expansion thought to have smoothed the cosmos. Some models even suggest that Horovà gravity could explain dark matter's effects, with modified gravitational laws at galactic scales replacing the need for invisible particles. Yet these tantalizing possibilities remain speculative, hinging on whether the theory's bold sacrifices align with nature's deepest rhythms. The debate over Horowa-Lifshitz gravity crystallizes a deeper tension in physics. How much symmetry are we willing to surrender in pursuit of quantum clarity? For now, the theory stands as a provocative thought experiment, a reminder that sometimes progress demands breaking the very rules we've long considered unbreakable. Whether it's a fleeting rebellion or a revolution in the making depends on whether the universe itself agrees that time, in the end, plays by its own rules. Neutron-star mergers aren't just cosmic fireworks, they're ultra-precise laboratories for testing gravity's most radical theories, and Horowa's foliation-based framework is no exception. When two neutron stars spiral into a cataclysmic collision, they send ripples through space-time that carry secrets about gravity's true nature. In Einstein's general relativity, these gravitational waves race outward at light speed, perfectly synchronized with any accompanying electromagnetic burst. But if Horowa gravity is correct with its rigid foliation of time and broken Lorentz symmetry, these waves might arrive out of sync, like a drummer missing a beat in an otherwise flawless orchestra. The key lies in the theory's preferred frame, an absolute reference for time that could subtly alter how gravitational waves propagate compared to light. Even a millisecond delay could betray the presence of physics beyond Einstein's vision. The smoking gun would come from multi-messenger events like GW 170,817, the landmark neutron-star merger detected in 2017. When gravitational waves and gamma rays from this collision reached Earth, their arrival times matched within seconds, tightening the noose around theories that predict significant dispersion. Horowa gravity's variations are more nuanced. Its higher-order spatial derivatives might only tweak wave propagation at extreme energies, leaving low-frequency signals largely unaffected. But future detectors, like the Cosmic Explorer or Einstein telescope, could spot deviations in the wave's higher harmonics or polarization patterns, subtle fingerprints of a universe where time doesn't flow as freely as space. Neutron stars themselves add another layer of scrutiny. These ultra-dense remnants are nature's perfect stress tests for gravity, packing a sun's worth of mass into a city-sized sphere. In Horowa's framework, their interiors might behave strangely. Equation of state calculations suggest that the theory's preferred frame could stiffen neutron star matter, altering their maximum mass or tidal deformability during mergers. Imagine squeezing a sponge that suddenly resists more than expected. Horowa gravity's foliation might make neutron stars less squishy when stretched by a companion's gravity, leaving imprints in the gravitational wave signal's amplitude and phase. Yet the theory isn't without escape routes. Some formulations introduce projectable conditions where the preferred frame's effects vanish in low-energy regimes, rendering it indistinguishable from general relativity in most astrophysical scenarios. Critics argue this feels like moving the goalposts, but supporters counter that all groundbreaking theories undergo refinement. After all, even Einstein's equations needed cosmological constants and dark matter to match observations. The real test will come when next-generation observatories peer deeper into the gravitational wave spectrum, hunting for anomalies that could reveal whether time's flow is as universal as we thought, or if it's quietly playing by different rules in the cosmic shadows. What if gravity isn't weaker than the other forces, it's just bleeding into hidden dimensions we can't see? That's the mind-bending premise of warped extra dimensions, where the fabric of reality isn't limited to the three spatial dimensions we experience. In this radical vision, gravity's puzzling feebleness, it's a trillion times weaker than electromagnetism, isn't a fundamental property but a cosmic illusion. The force might be just as strong as the others, but its influence is diluted as it leaks into higher dimensional space, like water seeping through cracks in a dam. The Randall-Sundrum model, proposed by physicists Lisa Randall and Raman Sundrum in 1999, paints a particularly vivid picture. Imagine our universe as a four-dimensional brain floating within a five-dimensional bulk. In this scenario, all particles and forces except gravity are trapped on our brain like ink confined to the surface of a sheet of paper, while gravity's carrier, the hypothetical graviton, can escape into the bulk. The kicker: the bulk isn't uniform, it's warped, with gravity's strength falling off exponentially as you move away from our brain. This warping creates a gravitational shadow on our brain, making gravity appear weak at large scales while potentially roaring back to full strength at microscopic distances. This isn't just abstract math, it has testable consequences. If extra dimensions exist, the Large Hadron Collider might produce microscopic black holes or Kaluza-Klein gravitons, higher dimensional echoes of the graviton that would decay into detectable particles. These wouldn't behave like ordinary matter. They'd carry missing energy or unusual momentum patterns, screaming clues about the hidden geometry of space. So far, the LHC hasn't spotted definitive evidence, but the search is far from over. Future collisions at higher energies could probe these elusive dimensions, or we might find indirect hints in cosmic rays carrying anomalous energy signatures. Skeptics argue that extra dimensions feel like a convenient escape hatch, a way to explain gravity's weakness without direct proof. But supporters counter that the math is too elegant to ignore. The Randall-Sundrum model, for instance, doesn't just tweak gravity, it solves the hierarchy problem, the maddening gap between gravity's scale and the other forces. By warping the extra dimension, the theory naturally generates this disparity without fine-tuning, like a cosmic funhouse mirror stretching reality's parameters into place. Whether warped dimensions are real or not, they force us to confront a thrilling possibility: that gravity's secrets aren't hidden in the forces we know, but in the dimensions we've yet to explore. The next time you drop a ball and watch it fall, consider this. Its journey might not be a straight line through space, but a curve through realms beyond our sight. Gravity's puzzling weakness isn't just a quirk, it's a cosmic mystery that keeps physicists awake at night. Imagine if the other fundamental forces were Olympic athletes, sprinting, lifting, and dominating their events. Gravity, by comparison, would be the spectator in the back row, barely able to lift a feather. Electromagnetism can yank a paperclip upward against Earth's entire gravitational pull, and the strong nuclear force outmuscles gravity by a factor of 10 to the 40. So why is gravity so feeble? One radical solution suggests it's not weak at all. It's just diluted, spreading its influence into unseen dimensions beyond our perception. This idea, known as the Randall-Sundrum model, paints a breathtaking picture. Our universe could be a four-dimensional membrane or brain floating within a higher dimensional bulk. While particles like electrons and photons are glued to our brain, unable to escape, gravity's carrier, the graviton, might be the ultimate wanderer leaking into the extra dimensions. Think of it like a game of cosmic hide and seek. The other forces are playing on the surface of a table, while gravity is the one sneaking underneath, its strength dissipating as it explores the space below. The warping of these extra dimensions could explain gravity's apparent feebleness. It's not that gravity is inherently weak, but that much of its power is lost in the higher dimensional void. But if extra dimensions are real, why haven't we spotted them? The answer might lie in their scale. Some theories propose these dimensions are curled up so tightly, smaller than an atom, that they're effectively invisible to our current experiments. It's like inspecting a garden hose from a distance. From far away, it looks like a one-dimensional line, but up close, you see the curled, circular dimension around its surface. If extra dimensions are similarly compactified, we'd need phenomenally precise instruments to detect them. the Large Hadron Collider has been hunting for signs of these hidden realms. If extra dimensions exist, high-energy collisions could produce microscopic black holes or Kaluza-Klein gravitons, higher dimensional echoes of gravity's messenger particle. These exotic phenomena would leave behind telltale energy signatures, like missing momentum in particle tracks or sudden bursts of radiation. So far, no definitive signal has appeared, but physicists aren't giving up. Future colliders with even greater energies might finally crack open dimensions we've only dreamed of. Yet skeptics raise a compelling counterpoint. If gravity leaks into extra dimensions, why hasn't this altered the orbits of planets or the behavior of stars in ways we can observe? The beauty of the Randall-Sundrum model is that it ingeniously sidesteps this issue. The warping of the fifth dimension creates a gravitational shadow near our brain, ensuring that gravity behaves normally at astronomical scales while only revealing its higher dimensional nature at extremely tiny distances. It's like living next to a waterfall, close enough to hear the roar but far enough that the mist never reaches you. The hierarchy problem, the staggering gap between gravity's scale and the other forces, finds an elegant solution in this framework. Instead of invoking arbitrary numbers or unexplained cancellations, the warped geometry naturally generates the vast disparity through the curvature of higher dimensional space. It's as if the universe folded its own parameters into the hidden creases of reality, leaving us to unravel them. Whether extra dimensions are real or not, their theoretical elegance challenges us to think beyond the confines of our everyday experience. The next time you feel gravity's familiar tug, consider the possibility that you're not just sensing the curvature of space-time. You might be brushing against the invisible contours of a far richer, far stranger cosmos. What if the universe operates by a single, elegant rule, one where size doesn't matter? That's the radical promise of conformal gravity, a theory where the laws of physics stay identical no matter how you stretch or shrink the cosmic ruler. Unlike Einstein's relativity, where mass warps space-time in a fixed way, conformal gravity treats scales as interchangeable, like a cosmic zoom button that leaves the underlying physics untouched. At its heart, this framework suggests that masses, planets, stars, even black holes aren't fundamental ingredients but emergent phenomena, arising dynamically from the universe's scale-invariant dance. Picture a fractal where every level looks the same, yet somehow complexity blooms from simplicity. The real shocker, conformal gravity, might explain one of astronomy's biggest headaches: galaxy rotation curves without invoking dark matter. In spiral galaxies, stars orbit so fast that conventional gravity says they should fly off into the void. Dark matter patches this by adding invisible mass, but conformal gravity offers a daring alternative. What if the mismatch isn't missing matter, but a misapplication of gravity's rules? The theory's equations, when solved for galaxy-scale dynamics, produce rotation curves that match observations almost perfectly. No halos of exotic particles, no unseen forces, just a tweak to how gravity behaves over vast distances. It's as if we've been trying to solve a puzzle with extra pieces when all along we were holding it upside down. Yet this elegant solution comes with thorny trade-offs. For conformal gravity to work, it must introduce a Weyl tensor, a geometric term representing gravity's sensitivity to spacetime's conformal structure. Critics argue this tensor feels like a mathematical fudge, grafting new physics onto Einstein's framework without a deeper mechanistic explanation. Worse, the theory struggles to replicate general relativity's triumphs closer to home. Solar system tests like Mercury's orbit or light bending around the Sun require fine-tuning to match observations, eroding the elegance that made conformal gravity appealing in the first place. The debate splits cosmologists. Supporters see conformal gravity as a paradigm shift, a way to unify quantum mechanics and gravity by treating mass as secondary to symmetry. Detractors call it a sleight of hand, trading dark matter's mysteries for ad hoc geometric terms. And then there's the elephant in the room. If conformal gravity is right, why does dark matter's evidence pile up in galaxy clusters and cosmic microwave background data? The theory's proponents counter that these observations might be reinterpreted, but the burden of proof remains heavy. Whether conformal gravity revolutionizes astrophysics or fades into obscurity, its bold reimagining of scale and mass forces us to confront a provocative idea: that the universe's deepest laws might not care about size at all, and what we call matter could just be patterns in a grander, more symmetrical design. The cosmos, in this light, isn't built from weights and measures, but from ratios and relationships, a tapestry where even the heaviest stars are just fleeting folds in the fabric. The Mannheim-Kazana's solution doesn't just tweak Newton's laws, it rewrites them entirely, proposing that gravity behaves differently on cosmic scales than in our solar system. At the heart of this idea is a radical reworking of Einstein's equations, introducing a new term that grows stronger with distance rather than weaker. Imagine throwing a ball and watching it curve more sharply the farther it travels, defying everyday intuition. That's the essence of this framework, a gravitational force that doesn't fade smoothly but gains strength in the vast expanses between stars, potentially explaining why galaxies rotate faster than expected without invoking dark matter. Central to this model is conformal gravity, a theory where physics remains unchanged regardless of scale, like a fractal that looks identical whether you zoom in or out. Mannheim and Kazana's applied this principle to galaxy dynamics, showing that their modified equations could replicate the flat rotation curves of spiral galaxies. In Newtonian physics, stars on the outskirts of a galaxy should slow down, just as planets farther from the Sun orbit more sluggishly. But Mannheim-Kazana's flips this logic. Their equations predict gravity's pull intensifies at galactic edges, keeping stars whirling at breakneck speeds. It's as if the galaxy's gravity has a hidden second wind kicking in just where conventional theories fail. Yet mainstream cosmologists aren't convinced. One major sticking point: the theory struggles to explain observations beyond spiral galaxies. While it might account for rotation curves, it falters with galaxy clusters, colossal structures where dark matter's gravitational fingerprints are unmistakable. Simulations show these clusters require vast amounts of unseen mass to hold together, something Mannheim-Kazana's can't easily replicate without ad hoc adjustments. Even more damning, the cosmic microwave background, the afterglow of the Big Bang, exhibits patterns that align precisely with dark matter's predicted influence. Without dark matter's gravitational scaffolding, the universe's large-scale structure becomes inexplicably lumpy, like a cake baked without flour. Another critique targets the theory's fine-tuning. To match observations, Mannheim-Kazana's introduces a new constant, the conformal parameter, which must be dialed to an absurdly precise value. Critics argue this feels less like a natural law and more like a fudge factor, retrofitting the math to fit the data rather than predicting it. Compare this to dark matter, which, for all its mystery, emerges naturally from particle physics theories like supersymmetry. Still, the theory's audacity earns respect. By daring to question dark matter's dominance, it forces physicists to scrutinize their assumptions. Could gravity's behavior at galactic scales truly differ from textbook predictions? Future tests like precision measurements of gravitational lensing around distant galaxies or anomalies in the James Webb Space Telescope's deep field images might tip the scales. Until then, Mannheim-Kazana's remains a provocative outlier, a reminder that even the most entrenched paradigms deserve challenges. After all, history's greatest breakthroughs often began as heresies. Einstein's general relativity has reigned supreme for over a century, but what if its equations are missing a hidden term, one that could unlock the universe's darkest secrets? Enter F of our gravity, a bold reimagining where the Ricci scalar, That crucial r in Einstein's field equations isn't just a fixed ingredient but a dynamic function, bending and twisting to fit the cosmos's wildest behaviors. Think of it like swapping a single musical note for an entire symphony. Suddenly, gravity's rules can adapt to explain everything from the universe's accelerating expansion to the invisible grip of dark matter, all without inventing new particles or energies. At its core, f of r gravity tweaks Einstein's framework by replacing the Ricci scalar with a custom-built function, f of r. This isn't just mathematical tinkering, it's a fundamental shift in how space-time responds to matter and energy. In general relativity, the Ricci scalar acts like a cosmic speedometer, measuring how space-time's curvature changes as matter moves through it. But in f of r gravity, this scalar becomes a flexible tool, amplifying or dampening gravity's effects depending on the environment. Picture a rubber sheet that stiffens when stretched too thin or softens under pressure, altering how objects roll across it. This adaptability lets the theory mimic dark energy's repulsive push, with certain choices of f of r generating cosmic acceleration without needing a cosmological constant. Einstein's greatest blunder turned modern enigma. But there's a catch. This flexibility comes at a price: ghostly instabilities. Many f of r models introduce Ostrogradsky ghosts, phantom fields with negative energy that lurk in the equations, threatening to unravel the universe's stability. These aren't just abstract bugs, they're mathematical red flags, signaling that the theory might allow impossible scenarios, like energy flowing backward in time or particles popping into existence from nothing. It's as if the universe's ledger suddenly permits negative balances, breaking the laws of cosmic accounting. Some theorists argue these ghosts can be exercised with careful tuning, like adding counterterms to the equations that cancel out the pathologies. Others see them as fatal flaws, proof that f of r gravity is more mathematical curiosity than physical reality. The debate gets even thornier when you compare f of r gravity to observational data. On one hand, certain f of r models elegantly replicate the universe's expansion history, matching supernova brightness and galaxy clustering without invoking dark energy. On the other, they often struggle with local tests like the precise orbits of planets or the bending of starlight, requiring convoluted screening mechanisms to hide their deviations from general relativity where we've measured it most precisely. It's like a theory that aces the final exam but fails the pop quiz, raising eyebrows about its true validity. Yet for all its challenges, f of r gravity remains a thrilling playground for theorists. By questioning whether Einstein's equations are the final word or just the first draft, it forces us to confront a deeper truth: that the universe's greatest mysteries might not demand new ingredients, but new recipes, ones where gravity itself is far more adaptable and far stranger than we ever imagined. Whether it's a stepping stone or a dead end, one thing's certain: the hunt for quantum gravity is anything but linear. Mercury's orbit holds secrets that could unravel even the most elegant alternatives to Einstein's gravity. This tiny planet, scorched by the sun's fury, traces a path through space that doesn't quite follow Newton's playbook, a subtle quirk Einstein famously explained with general relativity's curved space-time. But for f of r gravity, Mercury isn't just a puzzle, it's a brutal litmus test. The theory's flexibility, which lets it mimic dark energy on cosmic scales, becomes a liability in our solar system, where exquisite precision leaves no room for deviation. At the heart of the challenge is Mercury's perihelion, the point in its orbit where it swings closest to the Sun. Over centuries, this perihelion slowly drifts, a phenomenon called precession. While Newton's gravity accounts for most of this drift caused by tugs from other planets, a tiny fraction remained unexplained until Einstein. General relativity nails this residual precession down to 43 arcseconds per century, a triumph confirmed by radar measurements to within a razor-thin margin of error. For f of r gravity to survive, it must match this precision without breaking a sweat, but the math isn't so forgiving. The trouble lies in f of r's extra terms, those tweaks to Einstein's equations that let it mimic dark energy. In deep space, these terms flex freely, bending gravity's rules to fit observations. But near the sun's intense gravity, they can't hide. The theory's modifications inevitably distort space-time's fabric in ways that would alter Mercury's dance, either over-predicting the precession or introducing new, unseen wobbles. To squeeze past this hurdle, f of r models resort to a cosmic sleight of hand screening mechanisms. These are mathematical tricks that suppress the theory's deviations from general relativity in high-gravity regions like the solar system, while letting them run wild elsewhere. One popular screening method, the chameleon mechanism, works like a gravitational chameleon, changing its behavior based on the environment. Near the sun, where matter is dense and gravity strong, the chameleon hides, making f of r virtually indistinguishable from general relativity. But in the diffuse voids between galaxies, it emerges, driving cosmic acceleration without dark energy. It's a clever fix, but critics argue it feels suspiciously convenient, like retrofitting a theory to dodge falsification rather than predict new phenomena. The stakes couldn't be higher. If f of r gravity can't explain Mercury's orbit without artificial screens, is it really a fundamental theory, or just a mathematical dress-up of Einstein's original? Supporters counter that all groundbreaking theories face growing pains. Even general relativity needed decades to pass its toughest tests, from light bending to black holes. Perhaps future refinements will reconcile f of r with solar system precision naturally, without resorting to chameleons or other contrivances. Yet Mercury's silent testimony isn't the only obstacle. Lunar laser ranging bouncing lasers off mirrors left by Apollo astronauts measures Earth-Moon distance with millimeter precision, another minefield for alternative gravities. Similarly, the Cassini spacecraft's radio tracking of Saturn's orbit constrains deviations from general relativity to less than 1 part in 100,000. For f of r to compete, it must navigate this gauntlet of precision without flinching. What makes this struggle so fascinating isn't just the clash of theories, it's what it reveals about science itself. A great idea must do more than explain the unknown. It must also bend to the known, honoring every whisper of data from the orbits of planets to the echoes of the Big Bang. Whether f of r gravity clears these hurdles or stumbles, Mercury's relentless drift reminds us that the universe's deepest truths aren't just written in the stars, they're etched into the delicate dance of the worlds closest to home. Einstein's general relativity is built on the idea that space-time is a dynamic, ever-changing fabric, but what if one crucial piece of that fabric was frozen in place? That's the radical simplicity of unimodular gravity, a theory where the determinant of the metric, the mathematical function that measures how space-time stretches and squishes, is locked into a fixed value. Imagine space-time as a stretchy rubber sheet, but with one rule. No matter how much you bend or twist it, the sheet's total area never changes. This constraint might sound like a minor tweak, but it reshapes gravity's equations in ways that could finally bridge the gap between Einstein's cosmos and the quantum world. At first glance, unimodular gravity looks almost identical to general relativity. It still describes planets orbiting stars and light bending around black holes with the same precision. But under the hood, the theory's fixed metric determinant alters how gravity couples to the quantum vacuum, the seething sea of particle-antiparticle pairs that flicker in and out of existence. In standard general relativity, this vacuum energy generates a cosmological constant, a term Einstein famously added and later regretted to balance the universe against collapse. But here's the catch. Quantum field theory predicts a vacuum energy so enormous it should accelerate the universe's expansion billions of times faster than observed. This cosmological constant problem has haunted physicists for decades. Unimodular gravity offers a sly escape hatch. By fixing the metric determinant, the theory effectively decouples gravity from the vacuum energy's absolute value, rendering it irrelevant to the equations. It's as if the universe quietly ignores the quantum chaos beneath its feet, focusing only on the changes in energy rather than its overwhelming total. But does this minimalist approach solve quantum gravity's deeper puzzles? Proponents argue that unimodular gravity's streamlined structure makes renormalization, taming those pesky infinities in quantum calculations, far more manageable. Without the full metric's freedom to fluctuate, problematic terms in the math cancel out naturally, like a cosmic accountant balancing the books. Critics, however, counter that the theory is too minimal. While it might sidestep the cosmological constant problem, it doesn't inherently explain dark matter, quantum entanglement's role in gravity, or the singularity inside black holes. It's like fixing a leaky roof but leaving the crumbling foundation untouched. The debate hinges on whether unimodular gravity is a stepping stone or a dead end. Some theorists see it as a clue that nature prefers elegance, that the universe's deepest laws are simpler than we've dared to imagine. Others insist that true quantum gravity demands a more radical overhaul, one that rewrites the rules rather than tweaking them. Yet, even if unimodular gravity falls short of a grand unified theory, its quiet rebellion asking what happens when we stop letting space-time flex in every possible way reminds us that sometimes progress lies not in adding complexity, but in strategically subtracting it. Unimodular gravity's elegant constraint locking the metric determinant doesn't just tidy up Einstein's equations. It rewires one of cosmology's most baffling puzzles, the cosmological constant problem. Picture this: quantum field theory calculates the vacuum energy, the seething background energy of empty space, to be around 120 orders of magnitude stronger than what we observe. That's like predicting a hurricane and getting a breeze. General relativity treats this energy as a literal constant, lambda, which Einstein famously inserted to balance the universe against collapse. But here's the rub: lambda's observed value is absurdly tiny compared to theoretical predictions, a discrepancy so glaring it's been called the worst theoretical prediction in the history of physics. Unimodular gravity sidesteps this headache by changing the rules of the game. Normally, the vacuum energy directly curves space-time, but in this framework, the fixed metric determinant acts like a cosmic filter, decoupling gravity from the absolute value of vacuum energy. Only changes in energy density like matter clumping into stars or galaxies affect space-time's curvature. It's as if the universe has selective hearing, tuning out the deafening roar of quantum fluctuations and only responding to meaningful whispers. This mechanism doesn't explain why the cosmological constant is small. It simply renders the question moot, like realizing your car's speedometer doesn't care about the ocean's depth. But does this solve the problem or just hide it? Supporters argue that unimodular gravity reframes the issue elegantly. If vacuum energy doesn't gravitate, its enormous theoretical value becomes irrelevant. Critics, however, point out that the theory doesn't address why the residual cosmological constant, the leftover curvature not tied to matter, matches the observed dark energy driving cosmic acceleration. It's like removing a broken fuel gauge but still needing to account for the car's actual speed. The debate spills into quantum gravity's broader quest. Some theorists see unimodular gravity as a clue that nature prioritizes relational physics where only differences in energy matter, not absolutes. Others worry it's a mathematical sleight of hand, trading one mystery for another. Yet for all its unresolved edges, the theory offers something invaluable: a fresh lens to scrutinize the universe's deepest enigmas, reminding us that sometimes the most profound answers lie not in adding complexity, but in strategically subtracting it. Quantum gravity doesn't just redraw space-time as a network of interconnected nodes. It suggests that the particles making up matter might themselves be vibrant disturbances in that very network, like musical notes emerging from the vibrations of a cosmic guitar string. At its heart, this theory proposes something radical. What we call electrons, quarks, or photons aren't independent entities floating through space, but dynamic patterns woven into the fabric of the graph itself. Imagine tossing a pebble into a spider's web. The ripples that travel along the silk aren't separate from the web. They are the web momentarily rearranged. Similarly, particles in quantum gravity could be localized excitations of the graph's connections, flickering into existence as the network's links shift and reconfigure. This idea flips conventional physics on its head. Instead of treating particles and space-time as separate, matter in a geometric container, quantum gravity blurs the line between the container and the contents. The theory's atoms of space don't just define distances and angles, they also encode the very stuff of reality. A fermion, like an electron, might arise from a specific twist or knot in the graph's connections, while a boson, like a photon, could be a wave-like disturbance propagating through the network's edges. Even more striking, the properties we associate with particles' mass, charge, spin, might simply reflect the graph's underlying symmetries and topology. It's as if the universe's entire menagerie of matter is just geometry in disguise, a cosmic origami folding itself into the particles we observe. The potential to unify matter and geometry here is staggering. In loop quantum gravity, spin networks describe space's granular structure, but particles remain somewhat external, like actors on a stage. Quantum gravity goes further, suggesting the actors are the stage, their performances inseparable from the scaffolding beneath them. This could resolve long-standing puzzles, like why the standard model's particles have the masses and charges they do. Instead of arbitrary numbers plugged into equations, these values might emerge naturally from the graph's dynamics, much like the pitch of a guitar string depends on its tension and length. Yet challenges loom. For all its elegance, quantum gravity struggles to explain how the smooth, continuous fields of quantum field theory, like the electron's probability cloud, arise from a discrete graph. Reconciling the graph's binary on-off connections with the fluidity of wave functions demands mathematical gymnastics, often requiring approximations that gloss over the theory's granular roots. And while the framework can reproduce certain particle-like excitations in toy models, scaling this up to the full richness of the standard model remains a distant dream. The theory's true test might lie in its predictions. If particles are indeed vibrations of the graph, their behavior could deviate subtly from conventional physics in extreme environments, like near black hole horizons or in the early universe's high-energy soup. Some models suggest these deviations could manifest as violations of Lorentz symmetry at ultra-high energies, or as anomalous particle interactions in dense quantum fluids. Detecting such effects would require experiments far beyond today's technology, but the payoff could be revolutionary. Proof that matter and space-time aren't just interacting partners, but different harmonies in the same quantum symphony. Whether quantum gravity ultimately succeeds or falters, it dares us to reimagine reality's building blocks not as occupants of space, but as expressions of it, a universe where the question, what is matter, dissolves into the deeper mystery of how geometry sings. Quantum gravity's vision of space-time as a dynamic web of connections isn't just a standalone idea. It could be the missing thread weaving together some of physics' most ambitious frameworks. Take loop quantum gravity, for instance. Both theories share a core philosophy: that space isn't smooth and continuous but granular, built from discrete quantum-scale building blocks. But where loop quantum gravity envisions space as a network of intertwined loops, quantum gravity strips things down further, constructing reality from abstract points and links. Imagine merging these perspectives. What if the loops themselves were emergent properties of a deeper graph, like whirlpools forming in a flowing river. The spin networks of loop quantum gravity could arise from quantum gravity's underlying lattice, with the loop's intricate braiding reflecting how the graph's nodes interact over time. This hybrid approach might resolve one of loop quantum gravity's lingering challenges, explaining how its woven loops give rise to the particles we observe. If those particles are vibrations or defects in the graph structure, as quantum gravity suggests, then matter and space-time could emerge from the same foundational fabric. String theory, on the other hand, seems like an unlikely partner at first glance. It trades discrete nodes for shimmering, higher-dimensional strings. But dig deeper and surprising synergies appear. String theory's holographic principle, where a lower-dimensional boundary encodes higher-dimensional physics, mirrors quantum gravity's potential to simulate complex phenomena through sparse connections. Some researchers speculate that the extra dimensions string theory demands could be emergent properties of the graph's topology, like how a two-dimensional crossword puzzle can hint at a three-dimensional shape when viewed from the right angle. Even the strings themselves might find a home in this framework, not as fundamental objects but as extended excitations of the graph's edges, vibrating across the network like plucked guitar strings. The real test of these mergers lies in their predictive power. Could a unified framework explain why the standard model's particles have the masses and charges they do, or why gravity is so weak compared to the other forces? Quantum gravity's minimalist structure offers a tantalizing possibility that these mysteries aren't accidents but inevitabilities baked into the universe's underlying graph. For example, if certain graph configurations are statistically favored, much like ice crystals forming in predictable patterns, they might naturally give rise to the forces and particles we observe. Combine this with string theory's mathematical richness or loop quantum gravity's rigorous treatment of geometry, and you might have a recipe for a true theory of everything, one where the universe's deepest laws aren't imposed from above but emerge from the humblest of beginnings, a web of connections humming with quantum potential. Yet formidable hurdles remain. Merging these frameworks means reconciling their divergent languages, translating loop quantum gravity's spin foams or string theory's brains into the graph's austere vocabulary. Worse, each theory has its own unsolved puzzles. Loop quantum gravity struggles with dynamics, string theory with testability, and quantum gravity with bridging the gap between its discrete roots and our smooth cosmic experience. The most promising path forward might lie in computational simulations, where hybrid models could be stress-tested in virtual environments. Picture a digital universe built from quantum gravity's rules, evolving until loop-like structures or stringy vibrations appear spontaneously, a cosmic game of patience where emergence does the heavy lifting. Whether these frameworks ultimately unite or diverge, their interplay highlights a profound shift in how we conceive reality. The dream of a theory of everything may not be about finding a single monolithic equation, but about uncovering the hidden resonances between seemingly unrelated ideas, like realizing that light and radio waves are both just different rhythms of the same electromagnetic dance. Quantum gravity, with its focus on connections both literal and metaphorical, reminds us that the universe's deepest truth might not live in the notes themselves, but in the spaces between them. From shimmering strings to pixelated loops, from holograms to cosmic bounces, the quest for quantum gravity has spawned a universe of possibilities, each more daring than the last. We've journeyed through 30 wildly different visions of reality, each claiming to hold the key to uniting Einstein's cosmos with the quantum realm. Some theories weave space-time from tiny vibrating strings dancing in unseen dimensions. Others imagine it as a network of interlocking loops or a chaotic quantum foam bubbling beneath our feet. There are frameworks where gravity isn't even a force, just an illusion emerging from entropy, entanglement, or the collective hum of abstract geometric shapes. And then there are the rebels, the ones that toss out space-time entirely, treating it as a cosmic mirage projected from some deeper, stranger structure. The sheer diversity of these ideas isn't a sign of confusion. It's a testament to human creativity when faced with nature's toughest puzzles. After all, if the answer were obvious, we'd have found it by now. But here's the thrilling part: the truth might not live in any single theory. Just as light can be both particle and wave, quantum gravity's final answer could be a tapestry woven from multiple threads, strings and loops, torsion and topology, all playing their part in a grander symphony we're only beginning to hear. Maybe space-time is granular and emergent, holographic and twisted, with each perspective revealing a different facet of the same underlying truth. So where does that leave us? On the edge of discovery, with more questions than answers, and that's exactly where science shines brightest. Every one of these theories, no matter how outlandish, is a stepping stone toward something deeper. And who knows, maybe the person who finally cracks quantum gravity's code is watching this right now. Maybe it's you. Which of these theories blew your mind the most? Was it the elegance of string theory's hidden dimensions, or the gritty realism of loop quantum gravity's space-time atoms? The audacity of holography, or the minimalist beauty of causal sets? Drop your thoughts in the comments. Let's geek out over the wildest ideas in physics together. And remember, the universe's greatest mysteries don't belong just to physicists in lab coats. They belong to anyone who's ever looked up at the night sky and wondered how it all really works. Stay curious, stay bold, and keep questioning. The next breakthrough might be closer than we think.